Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, the lights grow softer, and the universe is allowed to take its time. Tonight we are going to drift toward one of the most dramatic events a galaxy can produce, although from a safe distance, which is generally the best distance from anything involving a black hole. Our subject is the tidal disruption event, often shortened to TDE, a name that sounds neat, technical, and reasonably well behaved. The reality is anything but. A tidal disruption event happens when a star wanders too close to a black hole, and the difference in gravity across the star becomes so powerful that the star can no longer hold itself together. What was once a steady sphere of glowing gas is stretched, pulled apart, and turned into a long stream of stellar material. Some of that material escapes, some swings back toward the black hole. As it moves, collides, heats, and circles, it can produce a sudden flare bright enough to be seen across immense distances. For a while, a black hole that may have been almost invisible announces itself by destroying something made of light. Before we move closer to that distant scene, let me ask you something simple. Where are you listening from tonight, and what time is it in your part of the world? Perhaps it is late and quiet. Perhaps you are listening during the afternoon and simply borrowing a little calm from the night. Maybe rain is tapping against a window, traffic is murmuring beyond the walls, or the room is so still that every small sound seems to have been promoted to management. Wherever you are, you're standing on a planet orbiting an ordinary star, inside a galaxy that almost certainly contains a massive black hole at its centre. That sounds alarming when said too quickly, so let us say it more gently. The black hole is very far away, it is not roaming through the Milky Way looking for snacks, and the sun is in no danger of suddenly sliding toward it. Galactic centres are busy places, but our solar system lives in a much quieter neighbourhood, where the most immediate danger is usually stepping on something in the dark. If you find these slow journeys through science relaxing, or if they give your thoughts somewhere peaceful to settle, you can give the video a like and subscribe to the channel. It helps this quiet corner reach other people who may also enjoy learning about the universe without being shouted at by it. And I do hope the story of a star being torn apart does not sound too energetic for bedtime. The science is violent certainly, but the telling does not need to be. We are not standing beside the event. We are receiving old light from very far away, examining it patiently and asking what it can teach us. So settle into whatever position feels comfortable, allow the day to loosen its grip a little, and let us begin with a star that has no idea its path is about to become very complicated. Picture a normal star moving through a galaxy. It may be similar to the Sun, smaller and cooler, or larger and hotter. It is held together by a long-running balance. Gravity pulls its material inward, while pressure generated by the hot interior pushes outward. For millions or billions of years, these two tendencies remain in a kind of working agreement. It is not a peaceful agreement in the everyday sense. The centre is hot enough for nuclear fusion, enormous amounts of energy are constantly moving outward, and the entire object is a sphere of plasma with weather that would make a hurricane look like a light draft. Even so, the star is stable. It maintains its shape, follows its orbit, and continues shining. From a distance, it is a simple point of light. Inside, it is one of nature's most successful balancing acts. Now place that star in the dense central region of a galaxy. Near a galactic centre, stars may crowd together much more tightly than they do in the quiet part of the Milky Way where the Sun resides. Orbits can be altered by close gravitational encounters. A star may pass another star, a compact object, or a cluster, and receive a small change in speed or direction. Usually that change is not disastrous. The star simply continues on a slightly different path, rather like someone leaving a busy railway station through the wrong exit and deciding it is probably fine. Occasionally, however, the new orbit carries the star toward the massive black hole at the galaxy's centre. A black hole does not need to chase the star. It does not reach out like a hand, nor does it pull everything in the galaxy toward immediate doom. A star can orbit a black hole at a safe distance, just as planets orbit stars. Gravity behaves normally outside the event horizon, and distance matters enormously. The problem begins only when the star passes close enough for the black hole's gravitational field to vary sharply from one side of the star to the other. The side facing the black hole feels a stronger pull than the side farther away. That difference is called a tidal force. Earth's oceans respond to tidal forces from the moon and sun, producing the familiar rise and fall of sea levels. The effect near a massive black hole is the same basic idea, with the volume turned up to a level no sensible ocean would recommend. At first, the star may only stretch slightly. Its shape begins to change as the near side is pulled more strongly and the far side lags behind. The star's own gravity tries to keep everything together. Pressure inside the star resists the deformation as well. Whether the star survives depends on many details, including the mass of the black hole, the density and structure of the star, and how closely the star passes. A dense stellar core may endure an encounter that would completely destroy a looser star. A shallow passage may strip away only the outer layers. A deeper one can overcome the star's self-gravity entirely. When that happens, the star is no longer a star in the usual sense. It becomes a stream. This stretching is often called spaghettification, one of those scientific terms that sounds as though someone became hungry during a meeting. The name is useful because the image is close to what happens. The star is pulled into a long, thin structure, compressed in some directions and extended dramatically in another. Yet it is worth remembering that this is not a neat strand of pasta moving politely around a plate. The material is extremely hot gas, and different parts of it are placed onto different paths. Some pieces gain enough orbital energy to escape the black hole's influence. Other pieces remain gravitationally bound and travel outward, only to return later. The once spherical star is divided into a long train of debris, with each section carrying a slightly different amount of energy. For the star, this change can happen with astonishing speed compared with its long life. A star may shine steadily for billions of years, and then be disrupted during a single close passage lasting hours. That contrast is part of what makes tidal disruption events so striking. They bring together two very different cosmic timescales. There is the slow life of the star, measured in millions or billions of years, and the sudden encounter, measured in minutes, hours, days, and months. It is rather like spending a lifetime carefully building a library and then discovering that gravity has strong opinions about shelving. The black hole itself remains dark. It does not light up because we can see the event horizon, or because the interior becomes visible. Nothing from inside the event horizon can send information back to us. The brightness comes from the stellar material outside. As bound debris returns, streams of gas may collide with one another. Those collisions convert orbital motion into heat. Material can begin forming a hot flow or disk around the black hole, although the exact process is complicated and can differ from one event to another. Radiation may emerge in visible light, ultraviolet light, X-rays, and sometimes radio waves. In rare cases, powerful jets may form and aim energetic particles outward at tremendous speeds. Astronomers do not see the black hole directly. They see the consequences of matter trying to move around it. This is one reason tidal disruption events are so useful. Many massive black holes spend most of their time in a quiet state. If little gas is falling toward them, they produce very little radiation and are difficult to notice, especially in distant galaxies. A tidal disruption event briefly changes that. The black hole receives a sudden delivery of stellar material, and the region around it becomes bright. For astronomers, the flare is like a temporary lamp switched on around an object that normally hides in darkness. By studying the brightness, temperature, spectrum, timing, and changes in that flare, researchers can estimate properties of the black hole and the destroyed star. The event is sometimes described as a black hole eating a star. That phrase is understandable, but it can be misleading if imagined too literally. The black hole does not swallow the entire star in one bite. Much of the material may never cross the event horizon. A large fraction can be thrown outward, while the rest returns over time. Even the bound material does not necessarily fall straight in. It must lose energy and angular momentum, circulate, collide, heat, and gradually move inward. Black holes may be famous for consuming matter, but they are not always efficient diners. They spill a remarkable amount, generate an enormous mess, and make the surrounding region glow so brightly that telescopes in another galaxy could, in principle, notice the disturbance. The word tidal in tidal disruption event is important because it explains the mechanism. The black hole's overall pull is not the only issue. A uniform gravitational pull would move the whole star together. Destruction occurs because the pull changes across the star's width. Your feet feel a slightly stronger gravitational attraction to Earth than your head does, since your feet are closer to Earth's centre. The difference is far too small to notice. Near a black hole, that gradient can become extreme. The near side accelerates more strongly than the far side, and the star is stretched beyond what its self-gravity can repair. There is a particular distance, often called the tidal radius, inside which disruption becomes possible. It is not a hard physical surface. No sign floats in space saying, "Stars beyond this point may lose their shape." It is a calculated boundary that depends on the size and mass of the star, as well as the mass of the black hole. A larger, puffier star can be disrupted farther out. A compact object such as a white dwarf, neutron star or stellar core can survive much closer before tides overwhelm it. The black hole's mass creates another interesting effect. A more massive black hole has stronger gravity, but its event horizon is also larger. For the most enormous supermassive black holes, a sun-like star may cross the event horizon before being visibly torn apart outside it. In that case, the event produces far less of the bright display astronomers usually associate with a tidal disruption. So the most observable TDEs often involve black holes within a certain broad mass range, massive enough to dominate the centre of a galaxy, but not so massive that the entire star disappears across the horizon before the disruption unfolds where light can escape. This gives astronomers a useful way to probe black holes that might otherwise be difficult to measure. Each event contains clues, but reading them is not simple. The flare depends not only on the black hole's mass, but also on its spin, the star's structure, the depth of the encounter, the direction of the orbit, and how the debris interacts. Nature rarely provides a clean laboratory experiment with one variable changed at a time. It prefers to alter everything together and then leave astronomers with several years of data analysis. From Earth, a tidal disruption event does not appear as a detailed picture of a star being stretched. Even our best telescopes cannot usually resolve the event directly. The host galaxy is far too distant, and the region involved is far too small on the sky. Instead, astronomers detect a new point of light near the centre of a galaxy. It brightens, changes colour, produces characteristic spectral features, and then fades. Different observatories monitor it at different wavelengths. Optical surveys may notice the first rise. Ultraviolet instruments measure the hot emission. X-ray telescopes look for radiation from material closer to the black hole. Radio telescopes may detect outflows or jets interacting with gas around the galactic centre. The process resembles medical diagnosis more than ordinary photography. Astronomers cannot stand beside the event and inspect it directly, so they collect symptoms. How quickly did the light rise? How hot is the emitting gas? Which atoms leave fingerprints in the spectrum? Does the X-ray brightness fluctuate? Is the flare exactly at the galactic centre, or slightly away from it? Does it fade smoothly, return in bursts, or remain bright for years? Each answer narrows the possibilities. A supernova can also produce a sudden bright flare. So can an active galactic nucleus, where a black hole already has a long-term supply of gas. The challenge is to distinguish a star being torn apart from other cosmic events that also have a talent for dramatic entrances. One of the appealing things about TDEs, scientifically speaking, is that they connect many areas of astrophysics at once. They involve stellar structure, because the internal density of the star affects how it breaks. They involve orbital mechanics, because the path determines the encounter. They involve general relativity, because the strongest effects occur near a black hole, where space-time is highly curved. They involve plasma physics and radiation, because the debris becomes hot, ionized, and luminous. They involve galactic astronomy, because the event occurs in the crowded environment around a central black hole. A single flare can become a meeting point for nearly every subject that enjoys making equations look slightly intimidating. Yet there is also a simple story beneath all that complexity. A star approaches a black hole. Gravity differs too much from one side of the star to the other. The star comes apart. Its material spreads into a stream. Some leaves, some returns. The returning matter produces heat and light. Astronomers detect that light much later and use it to reconstruct what happened. The event is extreme, but the logic begins with the same kind of tidal effect that raises oceans on Earth. The difference lies in scale. That scale can be difficult to hold in the mind. A sun-like star is already enormous. More than 1 million Earths could fit inside the volume of the Sun. Its mass is strong enough to hold an entire planetary system in orbit. Now imagine a gravitational gradient capable of overcoming the star's own gravity and pulling that vast body apart. The black hole may contain the mass of millions of suns concentrated within a region small compared with the galaxy around it. The encounter does not require contact with the surface, because a black hole has no solid surface in the ordinary sense. The destruction begins in empty space, governed by the shape of the gravitational field. The star may not know, in any meaningful physical sense, that a boundary has been crossed. There is no sudden wall or flash at the tidal radius. The deformation simply grows. At first, the outer layers shift, then the entire star lengthens. Internal pressure waves move through the gas. The core struggles to remain bound. Depending on the encounter, the star may be fully disrupted or only partly stripped. In a partial event, a surviving core can continue on a changed orbit, perhaps returning later for another damaging passage. That possibility is especially interesting because it turns what sounds like a single catastrophe into a repeating process. A star may lose material again and again, each orbit carrying it back toward the same black hole. Complete disruptions create their own sequence. After the initial encounter, the debris does not instantly settle into a tidy disk. It follows elongated orbits. Relativistic effects can rotate those orbits, causing streams to intersect. Collisions may produce shocks, heating the gas and changing its motion. Winds can carry material outward. Light from the inner regions can be absorbed and reprocessed by gas farther away, changing the wavelengths we observe. This helps explain why different tidal disruption events can look surprisingly different, even though the basic cause is the same. Some glow strongly in X-rays, suggesting we are seeing very hot material close to the black hole. Others are brightest in visible and ultraviolet light, perhaps because surrounding debris absorbs higher energy radiation and releases it again at longer wavelengths. A few produce relativistic jets, narrow beams of particles and radiation that can make the event appear especially bright when one points roughly toward Earth. Most do not. There is no single perfect TDE template that every event politely follows. There are families, patterns, exceptions, and a growing number of objects that seem determined to keep astronomers humble. These flares also allow scientists to study black holes that are not actively feeding most of the time. At the center of many galaxies, a supermassive black hole may sit in relative quiet, surrounded by stars but receiving little gas. It leaves only subtle evidence of its presence through the motions of nearby objects. Then a star enters the wrong orbit. For several months or years, the hidden black hole becomes the center of a bright transient source. Its gravity has not changed. Its appetite has not suddenly awakened as a conscious choice. The environment has changed because fuel has arrived. That distinction matters. Black holes are often described as if they are endlessly hungry, but a black hole cannot consume what does not come near it. Most stars in a galaxy will never approach the central black hole closely enough to be disrupted. Space is large, stable orbits are common, and even crowded galactic centers contain far more empty volume than solid matter. TDEs are rare for any individual star. Their value comes from the vast number of galaxies and the growing ability of sky surveys to monitor huge areas repeatedly. The universe may stage these events infrequently in one location, but there are many locations to watch. Modern surveys have turned the night sky into something closer to a continuous film than a collection of occasional photographs. Telescopes return to the same regions again and again, looking for anything that changes. A point of light appears where none was recorded before. Computers compare images, identify the new source, and alert astronomers. Other telescopes then turn toward it. The event may have begun hundreds of millions or billions of years ago, but from our point of view, the light has just arrived. We are not watching the star die in the present. We are receiving a delayed report carried across space at the speed of light. There is something useful in keeping that delay in mind. Astronomy is always an examination of the past. The moon appears to us as it was a little over a second ago. The sun appears as it was about 8 minutes ago. Distant galaxies arrive in our telescopes after journeys lasting millions or billions of years. A tidal disruption event may already be ancient by the time a survey detects its first photons. The black hole may have returned to silence. The debris may have cooled and dispersed. The galaxy may have continued changing. Yet the light preserves a sequence, and by collecting it carefully, we can replay part of the event. To understand what a tidal disruption event really is, it helps to set aside the familiar picture of a black hole simply swallowing a star whole. That image is dramatic, easy to remember, and usually much too tidy. A real encounter is a sequence of gravitational changes involving the star's structure, its orbit, the mass of the black hole, and the way different parts of the star respond as they pass through an increasingly uneven gravitational field. The star does not touch a solid surface, because there is no solid surface waiting for it. It is not struck by anything, and the black hole does not suddenly switch on a special destructive force. The star is pulled apart because gravity becomes noticeably stronger across the distance from its far side to its near side. Once that difference becomes greater than the star's ability to hold itself together, the balance that has preserved the star for millions or billions of years begins to fail. That failure is the central event hidden inside the compact name TDE. The word tidal can make the process sound almost gentle. We usually associate tides with shorelines, fishing boats, wet shoes, and the discovery that the beach towel was placed considerably closer to the water than expected. The tides on Earth are created mainly because the moon's gravity pulls more strongly on the side of Earth closest to it than on the side farther away. The difference across our planet slightly stretches the oceans and Earth itself. A black hole creates tidal forces for the same reason, although the changing gravity near it can be enormously greater. A star approaching a massive black hole may span hundreds of thousands or millions of kilometers. When the near side of that star is significantly closer to the black hole than the far side, the two sides no longer experience nearly the same gravitational acceleration. The near side begins falling faster, the far side falls more slowly, and the star is stretched along the direction pointing toward the black hole. At the same time, it may be squeezed in directions across that line, producing a rapidly changing, highly distorted stellar shape. Ordinary gravity pulls the star as a whole toward the black hole. Tidal gravity pulls different parts of the star differently, and that distinction is what causes the damage. You can imagine carrying a soft loaf of bread while someone pulls both ends apart. If both hands move together at exactly the same speed, the loaf travels without changing shape. If one hand pulls much harder than the other, the loaf stretches and eventually breaks. The comparison is imperfect, mostly because a star is not bread, and the kitchen would need to be several million kilometers wide, but the principle is useful. A tidal disruption does not depend only on how strong gravity is at one point. It depends on how quickly the strength of gravity changes from one point to another. The star enters the encounter with its own gravity working to preserve it. Every parcel of gas in the star is attracted toward the rest of the star, and the dense central regions are bound much more firmly than the thin outer layers. Pressure also supports the star from within. Energy produced in the core works its way outward, and the hot gas resists compression. During ordinary stellar life, these effects create a stable object. Near a black hole, however, the external tidal force grows rapidly as the distance decreases. At some point, depending on the specific star and black hole, the external difference in gravity can match and then exceed the star's internal self-gravity. Astronomers call the approximate distance where this becomes possible the tidal radius. The tidal radius is not identical for every encounter. A large, low-density star can be disrupted farther from a black hole than a small, dense star. A red giant, for example, has an extended outer envelope that is relatively weakly bound, so its outer layers may be stripped while its compact core survives. A main sequence star like the Sun is more concentrated, but it can still be completely destroyed if it passes deeply enough within the dangerous region. A white dwarf is so compact that it must come extremely close to a black hole before tides overcome its self-gravity, and such an encounter generally requires a lower mass black hole if the disruption is to happen outside the event horizon. In every case, the result depends on a competition between two gravitational systems, the star trying to remain one object, and the black hole producing a steep difference in force across it. A useful way to describe the depth of the encounter is to compare the tidal radius with the star's closest approach to the black hole. Astronomers often use a quantity called the penetration factor. Without turning bedtime into an unexpected mathematics examination, the idea is simple. If the star only brushes the outer part of the tidal region, the encounter is shallow. It may lose some material and escape with a surviving core. If it passes much more deeply inside, the encounter is stronger and complete destruction becomes more likely. The star's internal structure matters as well. Two stars with the same mass and size can respond differently if one has more of its mass packed toward the center. The black hole is therefore not operating a universal star-shredding machine with a single setting. Each event is shaped by the kind of star arriving, the exact orbit it follows, and the geometry of the encounter. This is why the phrase "a black hole tears a star apart" is accurate but incomplete. The star is not necessarily torn from one end like fabric. The entire body responds to the tidal field. Pressure waves move through the stellar gas. Layers accelerate at different rates. The shape changes, the density changes, and the internal motions can become extremely complicated. For a brief period, the star may be compressed in certain directions even while it is being stretched in another. In deep encounters, this compression can heat the stellar material sharply. Computer simulations are needed to follow the hydrodynamics because the gas is flowing, colliding, expanding, and reacting to both the black hole and its own changing gravity at the same time. Scientists understand the broad physics of the initial disruption fairly well, but the exact details can vary enough to keep powerful computers occupied and researchers supplied with very large coffee mugs. Once the star can no longer remain gravitationally bound as a single body, it becomes a long stream of debris. The material is spread across a range of orbital energies. Before disruption, nearly all parts of the star were travelling together on roughly the same path around the black hole. During disruption, the tidal field gives slightly different gravitational experiences to different parts of the star. Material closer to the black hole tends to lose orbital energy and becomes more tightly bound to it. Material on the far side tends to gain energy and may become unbound. The original star is therefore divided, not into two clean halves, but into a continuous stream whose different sections have different future paths. In a simplified version of a complete disruption, roughly part of the stellar debris remains bound to the black hole, while another part escapes on open trajectories. That division is often described as about half and half, although real events need not divide themselves with such administrative neatness. The escaping material travels outward into the galaxy, carrying elements that were once part of the star. The bound material also moves outward at first because its orbit is extremely elongated. Then gravity slows it, turns it around, and brings it back toward the black hole. The most tightly bound material returns first. Material with less binding energy travels farther away and takes longer to come back. Instead of the black hole receiving the entire star at once, the debris returns over an extended period. That returning stream is known as fallback material. The fallback rate, meaning how quickly mass comes back toward the black hole, is one of the most important ideas in TDE physics. In the simplest theoretical model, the rate eventually declines according to a predictable mathematical pattern, often described using a power law. Early researchers hoped that the fading light from a tidal disruption would closely follow this fallback rate, giving astronomers a clean signature of the event. Nature, as usual, read the proposal and added several complications. The light we observe depends not only on how much material returns, but on how efficiently that material collides, forms an accretion flow, releases energy, drives winds, and allows radiation to escape. The fallback supply is fundamental, but it is not always a direct copy of the observed brightness. A common misconception is that all returning gas immediately drops through the event horizon. Most of it has angular momentum, which is simply a measure of its orbital motion. The star did not fall straight toward the black hole from a stationary position. It approached on a curved path, often at very high speed, and the debris inherits that motion. Just as Earth does not fall directly into the Sun because it is moving sideways around it, the returning stellar material tends to travel around the black hole rather than directly inward. To be swallowed, it must lose energy and rearrange its angular momentum. This requires interactions within the debris. The returning stream may pass near the black hole, swing around it, and head outward again. General relativity changes the orientation of the orbit slightly during each close passage. This relativistic precession can cause the outgoing stream to cross paths with incoming material. When streams collide, shocks convert some of their ordered orbital motion into heat. The gas can lose energy and begin settling into a more circular configuration. This process is called circularization, because the highly stretched debris orbits gradually become part of a rotating flow around the black hole. How quickly circularization occurs is still an active area of study. In some events it may happen efficiently. In others, the debris can remain on eccentric orbits for a considerable time, bumping, shocking, and rearranging itself with all the elegance of several extension leads placed in the same drawer. Eventually, at least some of the material may form an accretion disk or a thick accretion flow. An accretion disk is not part of the black hole itself. It is hot matter orbiting outside the event horizon. Friction, magnetic fields, turbulence, and other processes allow material in the disk to move inward gradually. As gravitational energy is converted into heat, the gas can reach very high temperatures and produce radiation. Depending on the event, astronomers may observe visible light, ultraviolet radiation, X-rays, or a combination of them. Some TDEs also produce radio emission when outflowing material interacts with gas around the black hole. A small number launch powerful relativistic jets, although jets are not a required feature of every disruption. NASA descriptions of the standard picture show one part of the debris escaping, another part returning, and the returning material eventually forming a hot structure capable of producing visible ultraviolet and X-ray emission. The distinction between the disruption and the flare is worth keeping clear. The disruption is the moment and process in which tidal forces destroy or strip the star. The flare is the electromagnetic signal produced by the aftermath. They are related, but they are not identical. A star can be disrupted before the event becomes bright enough for distant telescopes to notice. Energy must be converted into radiation, and that radiation must travel through the surrounding debris. Some light may be absorbed and emitted again at different wavelengths. Winds launched from the accretion flow can form an extended envelope around the black hole, hiding the hottest inner regions from certain viewing angles. As a result, two similar disruptions may look quite different to observers. Orientation plays an important role. If an event produces a jet pointed near Earth, the radiation can appear exceptionally intense because the emission is concentrated and relativistically beamed in our direction. From another angle, the same event might look much less dramatic. If thick debris surrounds the black hole, an observer looking through that material may see cooler visible or ultraviolet emission rather than direct X-rays from the hottest inner flow. The black hole, star and observer form a three-dimensional arrangement, and we receive only one view. Astronomers must often work backward from that limited view, rather like trying to identify an entire restaurant by examining one takeaway receipt. Not every black hole can produce a bright disruption of every type of star. This may sound surprising because more massive black holes have stronger gravitational fields, but the size of the event horizon grows with the black hole's mass. For a sufficiently massive black hole, the event horizon can lie outside the distance where a sun-like star would otherwise be tidally torn apart. The star may then cross the horizon, largely intact from the perspective of an outside observer, giving the surrounding universe little time to receive a bright flare from disrupted debris. This is sometimes called direct capture. Black hole spin can change the relevant boundaries and allow disruptions under conditions that would not be possible for a non-spinning black hole of the same mass, which makes the upper mass limit more complicated than a single fixed number. Most of the classic TDE picture involves massive or supermassive black holes in galactic centers. These objects can contain hundreds of thousands, millions, or billions of times the mass of the Sun. Yet a TDE is not defined simply by the black hole's address. In principle, any sufficiently close encounter in which a black hole's tides overcome a star's self-gravity belongs to the same general family. White dwarfs may be disrupted by intermediate mass black holes. Stellar mass black holes can interact tidally with certain kinds of stars under suitable conditions, although the observational outcome may differ from the familiar galactic center flare. Researchers are especially interested in unusual disruptions because they may reveal black holes in mass ranges that are otherwise difficult to detect. The event horizon still remains central to the story, but it is not what tears the star apart. The event horizon is the boundary beyond which nothing, including light, can return to the outside universe. Tidal disruption usually begins outside that boundary, where radiation can still escape. A star can therefore be destroyed without any of its material having crossed the horizon yet. This separation is important because it explains how astronomers can see such a brilliant event associated with an object that emits no light of its own. Everything observable is happening outside the black hole. The glowing gas, shocks, disk, winds, and jets all occupy regions from which signals can still travel outward. You might reasonably wonder whether the black hole notices the meal. In terms of total mass, a single star may be a very small addition to a supermassive black hole. A black hole containing several million solar masses does not change dramatically after receiving part of one star. Its mass increases slightly, its spin may change by a tiny amount, and then it continues existing much as before. The surrounding region, however, changes enormously. A previously quiet galactic nucleus can brighten by a remarkable amount. This is why TDEs are sometimes described as temporarily awakening dormant black holes. The black hole was never asleep in a literal sense, but it lacked a strong supply of matter. The disruption provides a sudden injection of fuel. That temporary nature helps astronomers distinguish TDEs from active galactic nuclei. An active galactic nucleus is powered by a central black hole that already has a more persistent supply of gas. Its brightness can vary, sometimes strongly, but it may remain active for long periods. A TDE generally rises and fades as a finite amount of stellar material is supplied. The distinction is not always obvious. Some events occur in galaxies whose centres already show activity. Others display repeated flares, perhaps because a surviving star returns on an orbit, or because the accretion flow behaves irregularly. Astronomers therefore combine location, spectrum, temperature, light curve shape, and observations across many wavelengths before deciding what they are seeing. A supernova provides another source of confusion. Both a supernova and a TDE can appear as a new, bright point in a distant galaxy. Both can change over weeks and months. Both can produce broad spectral features and powerful outflows. The key difference is the engine. A supernova comes from the destruction or explosion of the star through internal stellar processes or a compact stellar interaction. A TDE is driven by an external tidal encounter with a black hole. TDE candidates are usually found very close to the centre of their host galaxies, where massive black holes are expected. Their spectra and temperatures can also differ from ordinary supernovae, and X-ray or ultraviolet behaviour may offer additional evidence. No single clue is always enough, which is why follow-up observations are so important. The name event can also give the impression of a brief flash lasting only seconds. In reality, the observable aftermath may unfold over months or years. The initial stellar passage is fast, but the most weakly bound debris takes longer to return. Accretion can continue after the peak brightness. Outflows travel into the surrounding environment and may produce delayed radio emission. X-rays can appear, disappear, or change as material shifts around the black hole. In some cases, observations reveal re-brightening long after the first flare. The word event therefore includes a whole evolving system, from the first disruption through the long decline of the debris supply. What makes this system especially valuable is that it begins from a comparatively sudden and limited delivery of matter. A quiet black hole is given a star or part of one, and astronomers watch how the surroundings respond. It is an astrophysical experiment that cannot be arranged deliberately, which is probably fortunate for nearby stars. Researchers can compare the rise time, peak brightness, temperature, spectral lines, X-ray output, radio behaviour, and long-term fading with theoretical models. From those comparisons, they try to infer the mass and spin of the black hole, the mass and type of the star, the depth of the encounter, and the efficiency with which the debris formed an accretion flow. Reviews of TDE science emphasize that these events provide rare opportunities to study massive black holes under rapidly changing feeding conditions and to examine matter in strong gravitational fields. Behind every light curve, however, lies an orbit. The star must somehow leave whatever stable path it once followed and enter a narrow region around the black hole where disruption becomes possible. Galactic centres contain many stars, but empty space still dominates, and a direct close approach is rare for any one of them. Something must place the star on what astronomers call a lost cone orbit, a path with so little angular momentum that it passes dangerously close to the central black hole. Gravitational encounters with other stars can gradually redirect it. Binary systems can be broken apart. The influence of a second black hole may disturb stellar paths. A galaxy merger can reshape the central environment and send new stars toward danger. Long before a star is visibly stretched, heated, or pulled into a stream, something much quieter has already gone wrong. Its orbit has changed. Perhaps the change was tiny at first, no more dramatic than a gentle gravitational nudge from another star passing nearby. Perhaps the star once belonged to a binary system and was thrown onto a new path when the pair passed close to the black hole. Maybe the centre of the galaxy contains an uneven distribution of stars, dense clouds, or even another black hole whose gravity slowly rearranged the surrounding orbits. Whatever the cause, The star has lost just enough sideways motion to bring it closer to the central black hole than before. It has not been dragged from the far side of the galaxy in a straight line. It has not been selected by the black hole or pulled from a safe orbit without warning. Instead, it has entered a narrow range of trajectories that astronomers call the loss cone, a collection of orbits that lead too close to the black hole for the traveller to return unchanged. The name loss cone comes from the way these paths can be represented mathematically. Imagine standing at a particular point in the crowded centre of a galaxy and considering every possible direction in which a star could move. Most directions lead to ordinary orbits that pass around the black hole at a comfortable distance. A small set points toward a much closer encounter. Those dangerous directions form something like a cone in velocity space. A star whose motion falls within that cone has too little angular momentum to stay far from the black hole. Angular momentum is what keeps an orbiting object from falling directly inward. Earth is constantly pulled toward the Sun, but it is also moving sideways quickly enough that it keeps missing. That continuous miss is an orbit. Reduce the sideways motion, and the path becomes more elongated. Reduce it far enough, and the next passage can carry the object very close to whatever it is orbiting. Near a galactic centre, stars do not move in perfectly isolated permanent tracks. They pull on one another. Each close passage makes a tiny adjustment to speed or direction. Most of these adjustments are harmless, and many cancel one another over time. Yet across thousands, millions, or even billions of orbits, those small gravitational interactions can gradually move a star into a dangerous trajectory. Astronomers call this process two-body relaxation. The term sounds restful, but it has little in common with the sort of relaxation we are aiming for tonight. It describes the slow redistribution of orbital energy and angular momentum as stars repeatedly disturb one another. A star can spend most of its existence moving safely through the galactic centre, only to have a sequence of minor encounters eventually turn its orbit into a long, narrow ellipse aimed toward the central black hole. This does not mean the star points directly at the black hole. Most tidal disruption events are expected to involve stars approaching on highly elongated orbits, often resembling parabolas during the close passage. The star sweeps inward, accelerates dramatically, curves around the black hole, and would normally head outward again. If the closest point of the orbit remained outside the tidal radius, that is exactly what would happen. The star might experience a strong gravitational encounter, but it would survive. The difference between survival and disruption may come down to a relatively small change in the distance of closest approach. In galactic terms, the safe and unsafe paths can lie remarkably close together. That closest point is called the pericenter, or sometimes the periapsis. It is the moment in the orbit when the separation between the star and black hole reaches its minimum. As the star moves toward pericenter, its speed rises. Gravitational potential energy is converted into motion, and the star may reach thousands or even tens of thousands of kilometers per second, depending on the mass of the black hole and the exact orbit. Even at those speeds, the black hole does not appear to rush toward the star. There is no solid body looming ahead, no dark wall filling the stellar sky. The black hole itself may occupy a surprisingly small region compared with the distances involved. What changes most, obviously, from the star's physical point of view is the gravitational field. Far from the black hole, the difference in gravitational pull between the near and far sides of the star is small. The entire star accelerates inward almost as one object. As the distance decreases, that difference grows rapidly. Gravity does not merely become stronger, it becomes more uneven. This side facing the black hole is closer, and therefore pulled more strongly. The centre feels a slightly weaker acceleration. The far side feels weaker still. This growing gradient begins to distort the star before it reaches the formal tidal radius. The boundary is an approximation, not a switch. Nothing clicks from safe to destroyed at a single perfect distance. The star responds continuously as the external tides rise. At first, the deformation may be modest. The star becomes slightly elongated along the direction toward the black hole. Its outer layers shift. Internal pressure and self-gravity react, attempting to restore the usual spherical shape. Stars are not rigid objects, so the response travels through them as waves in the hot gas. Different layers have different densities and may react at different rates. The diffuse outer envelope can be disturbed before the dense central regions. If the encounter is shallow, the outer gas may be stripped while the core remains intact. If the passage is deeper, the entire star is brought into the black hole's tidal grip. It is easy to think of the star as a single object making a single decision: survive or break. In reality, each region of the star follows the local forces acting upon it. The near side begins accelerating ahead of the centre. The far side falls behind. The stellar material is connected by pressure and gravity, but those connections can only transmit force so quickly. There comes a stage when the encounter proceeds faster than the star can adjust as a unified body. The star's internal communication, carried through pressure waves, cannot keep pace with the rapidly changing tidal field. From that point onward, the material begins behaving less like one stable star and more like many connected pieces moving on slightly different orbits. The star has lived for perhaps billions of years by maintaining hydrostatic equilibrium. Gravity has pulled inward while internal pressure has pushed outward. Every layer has settled into a balance with the layers above and below it. During the close approach, that arrangement is disturbed by an external force that changes sharply across the stellar diameter. The near side is no longer supported in quite the same way as the far side. The star is not simply compressed or expanded evenly. It is stretched in one direction and squeezed in others, creating a rapidly changing shape that ordinary stellar structure was never designed to maintain. A comparison with ocean tides can still help, provided we remember the enormous difference in scale. The moon races tides on Earth because its pull differs slightly across our planet. Earth remains intact because the difference is weak compared with the forces holding the planet together. Near a black hole, the same basic effect can become powerful enough to overcome the self-gravity of a star. Imagine the oceans rising not by a few meters, but continuing upward until the entire planet began to lengthen. Then replace the rock and water with plasma, increase the mass to that of the sun, and move the whole arrangement at a significant fraction of the speed of light. At that point, the usual seaside comparison has become somewhat ambitious, but the origin of the force remains the same. The black hole's mass determines much of what happens, though not always in the way we might expect. A black hole containing a few million times the mass of the Sun can disrupt a Sun-like star outside its event horizon, leaving enough room for the debris to produce a visible flare. A much larger black hole has a larger event horizon. For the most massive examples, a star may cross that horizon before the tidal forces pull it apart in a region visible to the outside universe. In that case, the star disappears with much less warning. The encounter is no less serious for the star, but it is less useful to distant astronomers because the disruption is hidden behind the point of no return. The mass and size of the star also matter. A red giant has a very extended envelope and a much denser core. Its outer gas is weakly bound and can be removed during a passage that leaves the core alive. A smaller main sequence star may respond differently because its material is packed more tightly. A white dwarf is denser still and can approach much closer before being disrupted. The phrase too close, therefore, has no single universal meaning. It depends on what is approaching, what it is approaching, and how quickly the orbit carries it through the dangerous region. As the star falls inward, its speed creates another counterintuitive feature of the event. The close encounter may last only a short time. A massive black hole can destroy a star through a process that unfolds over hours, even though the star's original orbit around the galactic center may have taken years, decades, or much longer. The final approach compresses an enormous change into a brief interval. The star spends most of the orbit far away, moving through relatively mild gravity. Then it races through pericenter, where the field changes faster and the tidal force reaches its peak. Suppose the star could somehow observe its surroundings. It would not see time stop or space turn into a visible funnel. Those common diagrams showing a black hole as a deep pit in a rubber sheet are useful for introducing curved space-time, but they should not be mistaken for the view from a window. The star would see the surrounding sky distorted by gravitational lensing. Light from background stars could be bent and magnified. The black hole's shadow might appear as a dark region surrounded by warped images, depending on the distance and orientation, yet the destructive force would be felt throughout the star's own body rather than arriving as an impact from outside. There would also be no sound travelling through space to announce the encounter. The star itself contains gas, so pressure waves and violent internal motion would occur within it, but no distant observer would hear anything directly. Astronomy receives light, particles, and sometimes gravitational waves, not a cosmic crash echoing across an empty vacuum. The violence of the event is reconstructed from radiation arriving much later. From Earth, the first obvious sign may come only after the star has already been torn into debris and some of that material has begun releasing energy. Before the bright flare, however, the orbit is doing something extremely important. Different parts of the star are being assigned different amounts of orbital energy. The side closest to the black hole sits deeper in the gravitational field. The far side sits slightly higher. During the disruption, that difference is effectively frozen into the debris. Material on one side becomes more tightly bound to the black hole, while material on the other side becomes less bound and may escape entirely. This energy spread is the reason the debris later separates into returning and departing streams. At the moment of closest approach, the star's centre follows one overall orbit, but the stellar material no longer shares one exact future. The near side can be placed onto a path that loops back toward the black hole. The far side can receive enough energy to leave on an open trajectory. Material between those regions fills a continuous range of energies and orbital periods. The star is not cut cleanly in half. It is distributed along a spectrum of possible paths, as though its single orbit has been separated into countless related versions. The transition from intact star to debris stream is often described with the frozen-in approximation. The idea is that once the star passes deeply enough into the tidal region, the energy differences imposed across it become set, and each part begins following an orbit determined mainly by the black hole. The approximation is useful, though the real gas continues interacting, compressing, heating, and responding to its own gravity. Detailed simulations reveal a much richer process, especially for deep encounters. Still, the basic picture explains why the star stretches into a long stream and why the returning material does not all come back at once. Deep passages can produce severe compression perpendicular to the orbital plane. The star is stretched lengthwise but squeezed vertically, rather like a very hot tube of toothpaste encountering an appliance no manufacturer considered during testing. This compression can raise the temperature and density inside parts of the star. In some theoretical cases, especially involving white dwarfs and lower mass black holes, the compression may become strong enough to trigger nuclear burning. For a typical main sequence star passing a supermassive black hole, the primary outcome remains gravitational disruption, but the internal shocks and heating still affect the debris. The star's rotation can influence the encounter as well. If the star spins in the same direction as its orbit around the black hole, parts of its surface already have motion that can either strengthen or weaken the tidal response. A star rotating in the opposite direction behaves somewhat differently. The orientation of the spin axis, the structure of the star, and any previous tidal deformation can change how material is removed. Two apparently similar stars can therefore produce different debris distributions even around identical black holes. magnetic fields are carried into the disruption too. Ordinary stars contain magnetic fields threaded through their plasma. As the star stretches, those field lines are stretched and compressed with it. At first, the magnetic field may be too weak to control the overall destruction, which is dominated by gravity. Later, as the debris orbits, collides, and begins forming an accretion flow, magnetic effects can become much more important. They help transport angular momentum, create turbulence, and perhaps contribute to the launching of jets. The flare seen months later can therefore depend partly on magnetic structures that were once hidden inside an ordinary star. The encounter may also alter the star before complete disruption occurs. Tidal forces can excite oscillations, causing the star to pulse and vibrate. Energy from the orbit is transferred into internal motion. During a near miss, these oscillations may continue after the star escapes, leaving it hotter, distorted, or rotating differently. If only the outer layers are stripped, the surviving core can carry the memory of the passage in its structure. It may become unusually luminous, chemically peculiar, or compact. Should its new orbit bring it back again, the second encounter will involve a star already changed by the first. For a complete disruption, there is no surviving central core to restore the original object. The stellar material remains continuous for a time, but the self-gravity that once maintained a sphere has lost its contest with the black hole's tidal field. The stream grows longer as different sections move at different speeds. The most bound debris takes a shorter orbit and will return sooner. The least bound material travels farther away. Unbound debris continues outward and may eventually mix with the gas of the galactic centre. Throughout this passage, the event horizon may still be much closer to the black hole than the star's orbit. This is important because it separates tidal destruction from direct capture. The star can be completely ruined while remaining outside the horizon. Light can still escape from the debris, information about the event can travel outward. Only later will some of the gas lose enough orbital energy to move inward and perhaps cross the horizon. The moment of disruption is therefore not the same as the moment of consumption. First, the star is dismantled. Then the debris begins a much longer and messier negotiation with orbital mechanics. An observer far away would not immediately know any of this was happening. The star may be too faint and distant to detect individually before the encounter. The black hole may be dormant, producing almost no radiation. The galactic centre appears quiet. Then the returning debris begins to interact, and the region brightens. By that time, the decisive passage is already over. Astronomers see the consequences and work backward, using the timing and colour of the flare to infer the orbit that caused it. This reconstruction is difficult because the original star vanishes as a recognisable object. Scientists cannot inspect it afterward and measure exactly how close it came. They use models. The observed rise time may indicate when the most tightly bound debris returned. The peak luminosity offers clues about how much energy was released. Spectral lines reveal the presence and motion of hydrogen, helium, and other elements. X-rays may come from very hot gas near the black hole, while visible and ultraviolet light may be produced farther out or reprocessed through surrounding material. Each measurement contains part of the orbital history. The host galaxy provides additional context. Its central black hole mass can sometimes be estimated from the motion of stars, the brightness of the galactic bulge, or other relationships between black holes and their host galaxies. With that mass in hand, astronomers can calculate the likely tidal radius for different kinds of stars. They can ask whether a Sun-like star would have been disrupted outside the event horizon, whether a giant's envelope is a better match, or whether the event may involve an unusual compact object. The star's final approach cannot be replayed directly, but the flare leaves enough evidence for a careful investigation. It is worth pausing over how narrow the dangerous route can be. The central black hole may influence stars across a large region, yet the tidal radius is tiny compared with the scale of the galaxy. A star must pass through a remarkably small target in three-dimensional space. This helps explain why TDEs are rare in any one galaxy. Most stars remain on stable orbits. Even those that move close to the centre usually miss the critical region. A disruption requires a particular combination of position, speed, and direction. Galactic dynamics can increase the odds. Dense star clusters produce more gravitational encounters. A non-spherical galactic centre can guide stars onto orbits that approach the black hole repeatedly. Giant molecular clouds and star clusters act as massive perturbers, changing stellar paths more efficiently than individual stars. If two galaxies merge, their central black holes may form a pair, and the shifting gravitational field can scatter nearby stars into dangerous trajectories. A binary black hole may increase the disruption rate for a time, though the exact behaviour depends on the masses, separation, and surrounding stellar population. Binary stars provide another route toward the centre. When a pair passes near a massive black hole, the black hole can pull the binary apart. One star may be thrown away at tremendous speed, becoming a hypervelocity star capable of escaping the galaxy. The other loses energy and becomes bound to the black hole on a tight orbit. This is known as the Hill's mechanism. The captured star may not be disrupted immediately, but later gravitational interactions can reduce its pericentre and bring it within the tidal radius. One member of the pair escapes into intergalactic space, while the other remains in the most dangerous neighbourhood available. It is not the most balanced division of travel arrangements. Some stars may circle the black hole many times before their final approach. Their orbits can be modified gradually, with the pericentre shrinking little by little. Others enter the lost cone through a single stronger encounter and plunge inward on the next passage. The route matters because it may affect the star's condition. Repeated near passes can heat or strip it before the final disruption. A sudden first encounter may involve a relatively undisturbed star. Astronomers cannot usually watch these earlier stages, but simulations show that the path into the tidal region can leave subtle signatures in the later debris. General relativity becomes increasingly important as the pericentre moves closer to the black hole. In Newtonian gravity, an elongated orbit follows a closed ellipse. Near a black hole, space-time curvature causes the direction of the orbit to rotate. The star does not return along exactly the same line after passing pericentre. This relativistic precession later helps debris streams collide, because the outgoing and incoming paths no longer align neatly. Black hole spin can also twist orbital planes through a process called frame dragging. A rotating black hole slightly drags the surrounding space-time with it, changing the motion of material on tilted orbits. During the star's first passage, these relativistic effects can alter how deeply it penetrates and how the debris is distributed. For most TDEs, the broad destruction can still be understood through tidal gravity, but accurate models need the relativistic corrections. This is especially true for close encounters and rapidly spinning black holes. The black hole's spin may determine whether the star is disrupted visibly, captured directly, or placed on a path that produces unusually strong stream collisions afterward. Despite all this complexity, the exact moment the star wanders too close is governed by a simple comparison. The black hole's tidal force across the star grows larger than the star's self-gravity. Until then, the star can respond and remain whole. Beyond that point, the material can no longer maintain one shared structure. The orbit has carried the star from a region where it belongs mainly to itself into a region where the black hole determines the motion of each part separately. There may be no clear instant when the star changes from one category to the other. The outer layers begin moving differently before the core gives way. The shape becomes more elongated with each moment. Internal waves and shocks pass through the gas. A shallow encounter may reach a maximum distortion and then relax as the star escapes. A deep encounter continues until recovery is impossible. Somewhere during that brief passage, the star stops being a stable sphere and becomes a stream whose sections are already separating onto different orbits. From far away, the black hole has done nothing visible yet. It remains dark, surrounded by a galaxy that appears unchanged. The flare will come later, after bound material travels outward, turns around, and returns. For the moment, the most important action is occurring inside the star itself. Gravity at the near surface is pulling ahead. Gravity at the far surface is falling behind. The centre is trying to hold the two together, but the distance between them is becoming dynamically meaningful. The star lengthens, narrows, and loses the internal balance that has lasted throughout its life. As the stellar material crosses deeper into the tidal field, ordinary language begins to struggle with the shape. Stretching is accurate but too mild. Break-in suggests a rigid object snapping in two, which is also wrong. The star is flowing, separating, and reorganizing under gravity, with every layer becoming part of a long distribution of gas. This is the stage that earned one of astrophysics' most memorable names. The star has reached the point where the difference in gravity does not merely disturb it. The difference reshapes it into something long, narrow, and increasingly unlike a star, and that takes us directly into the physical process known as spaghettification. Spaghettification begins when the star can no longer move through the black hole's gravitational field as one connected object. Until this stage, the star's self-gravity and internal pressure have continued trying to preserve its familiar spherical form. The attempt does not fail everywhere at exactly the same instant. The outer layers respond first because they are less tightly bound. Dense material near the centre resists for longer. Yet as the star moves farther inside the tidal region, the difference in gravitational acceleration across its diameter becomes too large for even the central regions to ignore. The side nearest the black hole accelerates ahead, the far side falls behind, and the star begins to lengthen along its orbit. This is the process that has been given the memorable name spaghettification, although the actual result is less like a tidy strand of spaghetti and more like a rapidly changing stream of extremely hot gas following thousands of slightly different paths. The name is often used when describing what would happen to a person falling toward a black hole, but the same underlying physics applies to stars. Gravity becomes stronger as distance decreases. If your feet were much closer to a black hole than your head, and if the gravitational field changed sharply enough across your height, your feet would accelerate faster than your head. You would be stretched from one end while being squeezed from the sides. A star experiences this across a far greater distance. A sun-like star is roughly 1.4 million kilometers wide. When one side of an object that large lies significantly deeper in the black hole's gravitational field than the other, the difference in acceleration can become enormous. The black hole does not need to touch the star. It does not have a physical hook, claw, or surface that grabs the stellar gas. The stretching occurs because every parcel of gas follows the curvature of space-time in its immediate location. Material near the front of the star is placed on one trajectory. Material near the centre follows another. Gas at the far side follows another still. While the star remains far away, these trajectories are similar enough for its own gravity and pressure to keep the material together. Near the tidal radius, the paths begin separating faster than the star can correct them. One way to picture this is to imagine a group of runners moving around a curved track. While they stay close together and run at nearly the same speed, the group maintains its shape. Now imagine that the runners at the front are suddenly accelerated. Those in the middle receive a smaller increase, and those at the back receive less again. The group stretches into a line. If ropes connected everyone, the ropes would tighten and resist for a while. Eventually, if the speed difference became large enough, the ropes would snap. In a star, gravity and pressure act rather like those connections. They are strong enough to preserve the star under ordinary conditions, but they have limits. The process is not limited to stretching. While the star lengthens in the direction toward and away from the black hole, it is compressed in directions perpendicular to that line. The gravitational paths of material on opposite sides of the star converge toward the orbital plane. This can flatten the star into a narrow shape during the deepest part of the passage. Some early descriptions compared the result to a pancake, while others preferred a squeezed tube of toothpaste. Astrophysics is unusually rich in food comparisons for a subject involving temperatures that would remove most kitchens from the property market. This compression can be extremely rapid. The upper layers of the star move downward toward the orbital plane while the lower layers move upward. Gas converges, pressure rises, and the temperature can increase sharply. The star may briefly become thinner in one direction, even as it grows longer in another. The exact degree of compression depends on how deeply the star passes within the tidal radius, how concentrated its mass is, and how the gas responds to the changing force. Hydrodynamic simulations show that shocks can develop as compressed layers collide and rebound. These shocks can limit the maximum compression and send energy back through the debris. It is important not to imagine the star as a rigid ball being crushed evenly. A star is a fluid body made mostly of ionized hydrogen and helium. Its material can flow, expand, compress, and form waves. Different layers contain different densities and temperatures. The outer envelope is relatively thin and loosely bound. The core is much denser and has stronger self-gravity. As the tidal field grows, these regions do not all respond in the same way. The surface can be drawn outward, while the core is still trying to remain compact. Pressure waves travel inward and outward. Material can move across the original stellar layers. By the time the disruption is complete, the neat organization that once defined the star has been thoroughly rearranged. The speed of the encounter makes the response more complicated. The star may spend millions of years orbiting in the galactic center, and only a few hours passing through the strongest part of the tidal field. Its internal structure cannot settle into a new stable balance during such a rapid event. Hydrostatic equilibrium, the balance between inward gravity and outward pressure that supported the star throughout its life, assumes that conditions change slowly enough for the gas to adjust. During a TDE, the external force may change faster than pressure signals can cross the star. The star is effectively caught before it can reorganize itself. There is a useful timescale inside every star called the dynamical time. It describes roughly how quickly the star would respond if its internal balance were disturbed. For the Sun, this timescale is on the order of an hour. That does not mean the whole Sun changes every hour. It means that pressure and gravity would need roughly that amount of time to carry out a large structural adjustment. During a deep tidal encounter, the strongest deformation can unfold on a comparable or shorter timescale. The star is therefore being altered almost as quickly as it is physically capable of responding. At first, the stellar gas remains connected. Even after the star has passed within the tidal radius, it may still look like an elongated object rather than a fully separated stream. The outer layers extend forward and backward along the orbit. The central region narrows. The star's own gravity continues acting between neighbouring parcels, delaying their separation. Eventually, however, the black hole's tidal field assigns sufficiently different velocities and energies to different parts of the star. The original body can no longer pull itself back together. That assignment of energy is one of the most important outcomes of spaghettification. Before the encounter, the star has one overall orbital energy around the black hole. Its individual atoms and parcels move internally, of course, but the star travels as a unit. During disruption, the near side falls deeper into the gravitational field than the far side. The material spread across the star therefore receives a range of orbital energies. Some gas becomes more tightly bound to the black hole, other gas becomes less tightly bound. A portion may gain enough energy to escape the black hole entirely. The result is not a clean division, where one half goes inward and the other half goes outward. Instead, the star becomes a continuous stream with a gradual energy distribution. At one end lies the most tightly bound debris. It will travel outward after the encounter, slow down, turn around, and return relatively quickly. Farther along the stream is material that is only weakly bound. It follows a larger orbit and takes longer to return. Beyond that lies unbound material that continues away from the black hole, and may never come back. The star's original centre lies somewhere within this stretch distribution, but it no longer acts as the centre of a stable stellar body. In a complete disruption, no gravitationally bound core survives. There is only gas distributed along the orbit. The stream can become many times longer than the original diameter of the star. As time passes, it may extend across distances comparable to the size of a planetary system. The material remains narrow in some directions, but it becomes increasingly spread out along its length. A shallow encounter can produce a different result. If the tidal force removes the outer layers without overcoming the gravity of the central core, the star undergoes partial spaghettification rather than complete destruction. Long streams are still pulled away, but the surviving core emerges from the passage. Its mass is reduced, its shape may be disturbed, and its orbit can change because the lost gas carries momentum. It may leave the black hole on a new trajectory, or remain bound and return for another encounter. We will spend more time with those survivors later, because escaping a black hole after losing part of yourself tends to create a rather unusual stellar biography. For a complete disruption, the depth of the passage affects how dramatically the star is squeezed. Astronomers often describe the depth using the penetration factor, which compares the tidal radius with the distance of closest approach. A penetration factor near 1 means the star passes close to the tidal boundary. A much larger value indicates a deeper plunge. Deep encounters can produce stronger compression and more complicated internal motion. They also bring the star into a region where general relativity has a greater effect on the orbit. Some theoretical studies have explored whether the compression can become strong enough to ignite additional nuclear reactions inside the star. During ordinary stellar life, nuclear fusion occurs under stable conditions in the core. A deep tidal compression can suddenly raise temperature and density elsewhere. In extreme cases, particularly when a white dwarf is disrupted by an intermediate mass black hole, the compression may trigger explosive nuclear burning. For ordinary main sequence stars disrupted by supermassive black holes, runaway burning is less certain and may occur only under unusual conditions. The star is already being destroyed by gravity, so nuclear reactions are not required to produce the TDE. They are a possible extra consequence in especially deep encounters rather than the standard engine behind every flare. The primary bright display usually comes later, when the debris interacts and begins releasing orbital energy. The immediate compression may generate shocks and some radiation, but that signal can be brief, faint, or hidden within the surrounding stellar material. The well-known flare that astronomers identify as a TDE is normally connected to the returning debris, stream collisions, outflows, and accretion around the black hole. Spaghettification prepares the material for that later activity by creating the long stream and determining which portions will return first. The stellar stream is not perfectly smooth. The original star contained density variations, convection, magnetic fields, and different chemical layers. These features are stretched with the gas. The core material, which has experienced nuclear processing, may occupy a different section of the stream from the original envelope. As the debris later returns and heats, the chemical signatures observed in its spectrum may provide clues about which layers of the star are being supplied to the black hole. Hydrogen and helium lines are commonly seen in TDE spectra, but their relative strength varies. Some events show strong helium emission and weak hydrogen, leading to questions about whether the destroyed star had already lost its hydrogen envelope, or whether radiation and gas conditions simply made helium easier to detect. The process of spaghettification determines how the stellar layers are mixed and distributed, but the observed spectrum also depends on ionization, temperature, density, and viewing angle. Reading the identity of the star from the later flare is therefore possible in principle, and difficult in practice, which is a familiar arrangement in astronomy. Magnetic fields are also stretched dramatically. A star's field may begin in loops and tangled structures embedded throughout its plasma. As the stellar material is drawn into a thin stream, the field lines are pulled along with it. This can amplify certain components of the magnetic field, much as stretching an elastic band stores tension. During the initial disruption, magnetic forces are usually too weak to stop the black hole's tides. Later, however, the field can influence how the debris behaves, particularly when the gas begins circulating around the black hole. Magnetic turbulence helps move angular momentum through accretion flows, allowing some material to drift inward while other material moves outward. Self-gravity does not disappear immediately after the star is disrupted. Neighbouring parts of the stream continue attracting one another. This can help keep the debris narrow as it moves away from the black hole. In some conditions, sections of the stream may become dense enough to form clumps. The balance between self-gravity, internal pressure, stretching, and heating determines whether the stream remains smooth or fragments. Simulations suggest that fragmentation may be possible, especially after the gas cools or if the original star had certain structural properties. These clumps would not usually reconstruct the original star. They are much smaller structures embedded in a long debris stream, and they continue following orbits determined mainly by the black hole. Their presence could make the later fallback rate irregular. Instead of gas returning in a perfectly smooth supply, dense knots might arrive separately and produce changes in brightness. Whether this is common in observed TDEs remains uncertain, but it illustrates how the destroyed star can continue carrying small-scale structure long after it loses its original shape. From the point of view of an observer travelling with the star's centre, the local experience would be unusual. According to general relativity, a freely falling object does not feel ordinary gravity in the same way that someone standing on a planet feels weight. The star's centre is in free fall. If the gravitational field were perfectly uniform across the entire star, every part would follow the same motion, and there would be no internal sensation of falling. The destructive effect comes entirely from the variation in gravity across the star. The centre follows one path while nearby material follows paths that converge or diverge. Tidal forces are therefore a local sign of space-time curvature. This helps explain why a very massive black hole can have surprisingly mild tidal forces at its event horizon compared with a smaller black hole. The event horizon of a supermassive black hole is enormous. At that large radius, gravity can change relatively gradually across the height of a person. Someone crossing the horizon of a sufficiently massive black hole might not be spaghettified at the boundary itself, although the tidal forces would grow deeper inside. Near a stellar mass black hole, the horizon is much smaller, and the gravitational field changes much more sharply across a human body. For a star undergoing a visible TDE, what matters is whether its tidal radius lies outside the horizon so that the disruption and resulting light can be observed. NASA similarly describes spaghettification as the stretching and squeezing caused by extreme tidal differences near black holes. A star near a supermassive black hole can be disrupted while still several event horizon radii away. The exact relationship depends on the masses involved. For black holes of millions of solar masses, a sun-like star can be torn apart outside the horizon. For black holes approaching hundreds of millions of solar masses, direct capture becomes increasingly likely, although black hole spin and orbital orientation can change the boundary. General relativity is especially important in close encounters because it affects both the disruption conditions and the future paths of the debris. The visual shape produced during spaghettification would also depend on the observer. From a distant viewpoint, light from the star is bent by the black hole's gravity. Images can be distorted, magnified, and delayed. Different parts of the stream may appear in more than one location, because their light follows different paths around the black hole. The stellar gas itself is moving at enormous speed, adding relativistic changes in brightness and colour. No telescope currently gives us a direct, detailed film of a distant star being stretched at the scale of the tidal radius. The familiar animations are scientific reconstructions based on calculations and simulations. Those simulations divide the star into many small elements and calculate how gravity, pressure, shocks, self-gravity, and sometimes magnetic fields change their motion. Early models used simplified stars whose pressure and density followed convenient mathematical relationships. More recent simulations use realistic stellar structures based on a star's mass, age, and evolutionary state. This matters because a young, low-mass star distributes its material differently from an older star with a dense helium core. The same orbit can completely disrupt one stellar model, while allowing another to retain a central remnant. The star's age can therefore decide how the spaghettification unfolds. A star early in its main sequence life may have a relatively simple internal structure. As it ages, fusion changes the chemical composition and density of the core. Later, when it becomes a subgiant or giant, the envelope expands enormously while the core becomes compact. Tidal forces can easily strip the extended envelope, but the core may pass through intact. What looks from Earth like a single class of flare may come from several very different types of stellar destruction. Rotation adds another layer. A spinning star already has material moving around its own centre. If the rotation lines up with the orbital motion around the black hole, it can reduce the effective binding of some regions and make disruption easier. Rotation in the opposite direction may offer slightly greater resistance. The black hole's tides can also spin the star up during the approach. As its shape changes, angular momentum is redistributed through the gas. By the time the star reaches its closest point, it may be rotating, stretching, and compressing all at once. If the star contains a companion, the situation becomes more complicated still. A binary star system approaching a black hole can be separated before either star reaches the tidal radius. One member may be thrown away, while the other is sent onto a close orbit. In rare cases, both stars could undergo disruptive interactions. Their debris streams might later meet or arrive at different times. Such events are difficult to model and identify, but they remind us that the simple picture of one isolated star approaching one isolated black hole is a starting point rather than a rule that every galactic center must follow. During the strongest part of an ordinary complete disruption, the star's identity disappears remarkably quickly. There is no explosion from the center outward like a conventional supernova. A supernova is usually driven by changes within the star, such as core collapse or runaway nuclear burning. Spaghettification is imposed from outside by the black hole's tidal field. The star is dismantled according to position. The near side, center, and far side are placed onto different orbits because they occupy different locations within the gravitational gradient. This produces a very different kind of stellar death. In a supernova, material can be thrown outward in nearly every direction around the star. In a TDE, the debris is initially concentrated into a narrow, elongated structure along the orbit. The geometry is strongly asymmetric. One tail may be unbound and head out into the galaxy. The other remains bound and will return toward the black hole. The process resembles the stretching of a small cosmic body into two tidal tails during a close gravitational encounter, but with far greater energy and with a star supplying the material. The unbound tail can leave the encounter at high speed. Its gas expands and cools as it travels outward. In principle, it can carry freshly processed elements from the stellar interior into the galactic center. The amount of material is small compared with the entire galaxy, but over many events, tidal disruptions may contribute some gas and chemical enrichment to the nuclear environment. The departing stream could also collide with surrounding interstellar material and produce weak delayed emission. The bound tail has a more complicated future. Immediately after pericenter, it also moves outward. The word bound does not mean it falls directly into the black hole at once. It means its orbital energy is not high enough to escape. Gravity slows it gradually. The most tightly bound end travels to a maximum distance and turns around first. Other sections continue farther before returning. This creates a natural ordering along the stream, with the earliest fallback material coming from one region of the original star and later material arriving from other regions. In the simplest calculation, the fallback rate eventually declines in a characteristic way because the debris has a particular distribution of orbital energies, yet the actual stream can be altered by stellar structure, internal shocks, self-gravity, relativity, and the details of the original orbit. The fallback pattern is not merely a clock started at the moment of disruption. It is a record of how spaghettification divided the star. By the time the first debris returns, the stream may be enormously long. The leading material is heading back toward the black hole while the trailing regions are still travelling away. Parts of what was once one star can be moving in opposite directions across a vast distance. There is no single location that can still be called the star. The original object has been replaced by an evolving orbital structure. The returning gas is also narrow enough that it may initially pass around the black hole without striking much else. If the orbit followed exactly the same path in and out, the stream could continue for several passages before losing enough energy to form a disk. General relativity prevents such perfect repetition. The direction of the orbit shifts during the close passage. When the debris comes around again, its path does not line up exactly with the outgoing stream. That misalignment prepares the conditions for collisions. Black hole spin can tilt and twist the returning paths further. If the stellar orbit is not aligned with the black hole's rotation, frame dragging may move the stream above or below its earlier plane. This can delay the first major collision, or cause intersections at different distances. The exact location of those intersections influences how much energy is released, how hot the gas becomes, and what type of radiation escapes. Spaghettification therefore does more than destroy the star. It establishes the initial conditions for everything that follows. It determines the energy spread of the debris, the thickness of the stream, the amount of mass that escapes, the fallback times, the chemical distribution, and the orientation of the returning gas. A small difference during the first few hours can change the flare observed months later. For the black hole, the encounter still delivered almost nothing across the event horizon. Most of the gas remains outside, travelling on extended orbits. The spectacular brightness associated with a TDE has not yet reached its full strength. The star has been taken apart, but its material has not settled into the hot rotating flow that can efficiently release gravitational energy. Destruction and feeding are separate stages. Imagine the scene after the closest passage. One end of the debris stream is racing away with enough energy to escape. Another remains attached only in the sense that gravity will eventually bring it back. Between them stretches the former star, no longer round, no longer in equilibrium, and no longer following a single orbit. Its gas forms a thin, curving line that continues lengthening as each section responds to its own energy and speed. The returning debris does not arrive as a compact object. It comes back as a long, narrow stream made from material that once occupied different layers of the star. The most tightly bound gas completes its extended orbit first, curves back toward the galactic centre, and approaches the black hole again. Farther behind it, other parts of the former star are still moving outward. Some will return days, weeks, months, or even years later. The least fortunate material, at least from the black hole's point of view, received enough energy during the disruption to escape entirely. This separation creates two broad tidal tails, one bound to the black hole and one unbound, although each tail contains a continuous spread of speeds, densities, temperatures, and orbital energies rather than a neat collection of identical parcels. At this stage, the star has completely lost its familiar shape. Nothing resembling a glowing sphere remains. The material can extend across an enormous distance, while staying surprisingly thin compared with its length. Self-gravity between nearby parts of the stream helps prevent it from expanding immediately in every direction. Internal pressure pushes outward, while the black hole's gravity continues stretching the material along the orbit. The stream becomes something like a very long tube of plasma, although even that description makes it sound more orderly than it is. Its width changes, its density varies, and different sections may heat, cool, compress, or form small irregularities as they travel. The bound debris has angular momentum, so it cannot simply fall straight through the event horizon. It approaches the black hole, swings around it, and begins moving outward again. If gravity behaved in a perfectly Newtonian way and nothing else interfered, the outgoing material might closely retrace the incoming orbit. It could continue looping along a highly elongated path without quickly becoming a circular disk. Near a massive black hole, however, general relativity changes the geometry of the orbit. The path rotates slightly during each close passage, an effect known as a tidal precession. The point of closest approach remains near the black hole, but the long axis of the orbit turns. That orbital shift is small in some encounters and substantial in others. It depends on how close the debris travels, the mass of the black hole, and the original path of the star. A deeply plunging stream around a massive black hole can experience strong precession. When it travels outward after the closed passage, it no longer follows exactly the same route it used while falling inward. The shifted outgoing stream may cross the path of material that is still arriving. Two sections of the same former star then meet at high speed. Calling this a collision is accurate, though it may suggest two solid objects striking each other. What actually meets are flowing streams of ionized gas. They can approach from different directions with relative speeds of thousands or tens of thousands of kilometers per second. When they intersect, shock waves form. Ordered orbital motion is converted into random thermal motion, which means the gas heats. Pressure rises, the stream becomes wider, and some material is redirected onto new orbits. The collision does not necessarily stop the gas or make it fall inward at once. Instead, it begins the gradual process of changing a narrow eccentric stream into a broader rotating flow around the black hole. This transformation is called circularization. The name makes it sound as though the debris quickly organizes itself into a perfect circle, perhaps after consulting a compass. Real circularization is less graceful. Gas must lose a large amount of orbital energy while preserving or redistributing angular momentum. Stream intersections, compression near pericenter, turbulence, magnetic stresses, and repeated passages may all contribute. Some material settles into less elongated orbits. Other material is pushed outward. A fraction may be launched away in winds. The flow can remain eccentric and irregular for many orbits, before it resembles the smooth accretion disks shown in simplified diagrams. How quickly circularization happens is one of the important unresolved questions in tidal disruption research. Early models often assumed that the debris would rapidly form a disk after returning to the black hole. Detailed simulations have shown that the answer depends strongly on the encounter. If relativistic precession causes a powerful collision close to the black hole, energy can be dissipated efficiently. If the streams meet far away at a shallow angle, the collision may be weaker. The gas can then remain on elongated orbits for a considerable time. Cooling, black hole spin, stream thickness, and the orientation of the orbit can all change the result. The first returning material passes through a narrow region near pericenter, where the stream is compressed vertically. Gas above and below the orbital plane is focused toward the middle, producing what researchers often call a nozzle shock. The image is similar to fluid being forced through a narrow opening. Though there is no physical nozzle sitting beside the black hole, gravity creates the focusing. The compression can heat and thicken the stream, potentially changing how it behaves during its next orbit. Exactly how much energy this shock removes from the debris remains debated, but it may help prepare the gas for later self-intersections by altering the stream's width and internal structure. A thicker stream has a greater chance of striking itself. Imagine trying to make two pieces of thread cross while moving them along slightly different paths. A tiny shift may allow them to miss. replace the thread with two wide ribbons, and an intersection becomes more likely. In a TDE, gas pressure, recombination, shocks and turbulence can broaden the returning stream. This may compensate for orbital effects that would otherwise move one section above or below another. The problem becomes especially complicated when the black hole is spinning. A rotating black hole does more than curve space-time through its mass. Its spin also drags the surrounding space-time slightly around with it. This effect, called frame dragging, can rotate the orbital plane of debris that is not aligned with the black hole's equator. Instead of every section remaining in one flat plane, the stream may be shifted upward or downward during successive passages. This nodal precession can delay self-intersection by causing the returning material to miss the outgoing stream. Later, as the stream widens or its path changes, a collision may finally occur. The delay matters because the amount of returning material changes with time. The fallback rate is usually highest relatively early in the event, after the most tightly bound debris completes its first orbit. If circularization is delayed, a large amount of gas can continue travelling on eccentric paths without immediately forming a compact accretion disk. Energy may still be released in shocks farther from the black hole, producing visible and ultraviolet light. Meanwhile, the hottest inner region may remain weak or hidden, which can help explain why some TDEs are optically bright, but produce less X-ray emission than simple disk models predict. Other events behave differently. Their debris may self-intersect close to the black hole, where orbital speeds are higher and the collision is more energetic. Gas can lose orbital energy quickly, forming a thick ring or disk-like structure. Temperatures rise, and radiation from the inner flow may emerge strongly in ultraviolet or X-ray wavelengths. Two disruptions involving similar stars can therefore produce very different signals because the streams collide at different places and angles. The material does not have to become completely circular before accretion begins. Even an eccentric flow can contain shocks, turbulence, and magnetic interactions that allow some gas to lose angular momentum and move inward. Accretion simply means that matter is gradually crossing smaller and smaller orbits toward the black hole. It does not require a thin, flat disk like the rings of Saturn. During the early phase of a TDE, the flow may be thick, uneven, tilted, and surrounded by winds. The familiar disk may develop later, after repeated interactions have made the orbits less elongated. As gas moves inward, gravitational energy is released. Matter farther from the black hole has more gravitational potential energy than matter orbiting close to it. When the debris descends into the deeper gravitational field, some of that energy becomes heat, motion, radiation, and magnetic activity. This is the source of the extraordinary brightness. The black hole itself remains dark. The event horizon is not glowing. What shines is the gas outside it, where material is compressed and heated before some fraction eventually crosses the horizon. An accretion flow can convert mass into radiation with impressive efficiency. Ordinary nuclear fusion in a star releases only a small fraction of the rest mass energy contained in its fuel. Accretion around a black hole can release a much larger fraction, depending on the black hole's spin and the orbit of the gas. This is why a relatively modest amount of stellar debris can produce a flare visible across a vast distance. The entire star does not need to be swallowed, and most of it does not need to release its energy at once. A sustained supply of returning material can keep the central region bright for months or longer. The earliest fallback gas is not necessarily the first material that reaches the event horizon. Returning and accreting are separate steps. The debris can come back to the black hole's neighbourhood and then spend time orbiting, colliding, and rearranging itself. If circularization is efficient, the delay between fallback and accretion may be short. If it is inefficient, gas can remain on large eccentric orbits, while the observable flare is powered partly by shocks rather than by matter near the event horizon. Astronomers try to separate these possibilities by comparing optical, ultraviolet, X-ray and radio observations. The stream also carries the chemical composition of the star. Material from the outer layers may be rich in hydrogen. Gas from deeper regions may contain more helium, nitrogen, carbon, and other products altered by stellar fusion. Because the debris returns in an order related to its original position and assigned orbital energy, the spectrum of the flare may change as different parts of the star arrive. In principle, this gives astronomers a way to examine the inside of a destroyed star. In practice, the spectrum is also affected by temperature, density, ionization, winds, and the angle from which we observe the event, so the stellar autopsy is not always straightforward. Spectral lines reveal motion as well as composition. Gas moving toward us shifts its light toward shorter wavelengths. Gas moving away shifts it toward longer wavelengths. Broad lines can indicate material travelling at thousands of kilometers per second. Their shapes may change as the debris distribution evolves. Some lines appear asymmetric, suggesting that parts of the flow are hidden, or that the gas is not arranged in a simple rotating disk. Others may be produced in an extended atmosphere of reprocessing material surrounding the inner accretion flow. Reprocessing occurs when high-energy radiation from near the black hole is absorbed by gas farther out and emitted again at longer wavelengths. Suppose the inner flow produces extreme ultraviolet or X-ray photons. A thick layer of debris or an outflow may intercept that radiation. The gas heats and then releases much of the energy as visible or ultraviolet light. From Earth, we may see a relatively cool, large emitting region, even though the original energy was generated much closer to the black hole. The debris acts rather like a lampshade, although one made from stellar plasma and moving fast enough to make ordinary household certification difficult. This surrounding material may be created naturally if the fallback rate is extremely high. Soon after disruption, debris can return faster than the black hole's accretion flow can process it efficiently. Radiation pressure builds as energy tries to escape through the dense gas. Some material may be blown outward in a wind. The black hole therefore receives only part of the returning star, while another part is expelled again. A TDE is less like a clean funnel, and more like a crowded transport system in which matter arrives, changes direction, collides, and occasionally decides to leave. These winds can carry a substantial amount of mass away from the black hole. They expand, cool, and become transparent over time. While dense, they can conceal the hottest inner regions. As the wind thins, X-rays that were previously absorbed may become visible. This can produce changes in the observed spectrum without requiring the black hole's feeding rate to change in exactly the same way. A flare may begin as a bright optical source and later reveal stronger X-ray emission as our view toward the centre clears. Viewing angle adds another complication. An observer looking down a relatively empty funnel above the accretion flow may see direct high-energy radiation. Someone viewing the same event through a thick layer of gas may see mainly reprocessed visible light. Since Earth receives only one line of sight to any distant TDE, astronomers must consider whether differences between events reflect genuinely different physics or simply different orientations. Most likely, both effects contribute. The unbound debris follows a separate story. After receiving positive orbital energy during the disruption, it continues away from the black hole. Its speed varies along the tail. Some material may move fast enough to cross the central region of the galaxy and interact with surrounding gas. Shocks produced by that interaction can generate radio emission, although the signal may appear well after the initial disruption. The tail spreads as it travels, carrying hydrogen, helium, and heavier elements into the galactic environment. Bound debris can also produce outflows that later collide with interstellar material. When a wind or jet pushes into the gas around the galactic nucleus, it drives a shock. Electrons are accelerated, magnetic fields are amplified, and radio waves can be produced through synchrotron emission. Radio telescopes may therefore continue observing a TDE after the visible and ultraviolet flare has begun fading. The radio behaviour helps researchers estimate the speed, energy, and geometry of the outflow. Most tidal disruption events do not produce a powerful relativistic jet, but a small number appear to do so. A jet is a narrow outflow launched from the region around the black hole, possibly through a combination of magnetic fields, accretion, and black hole spin. Material in the jet can travel close to the speed of light. When one points toward Earth, relativistic beaming makes the source appear exceptionally bright and variable. Such events are rare, either because jets are not always produced or because their narrow beams usually point elsewhere. Creating a strong jet may require the accretion flow to organise a large-scale magnetic field near the black hole. The original star contains magnetic fields, but whether those fields can be stretched, amplified, and arranged quickly enough is still under investigation. Turbulence in the accretion flow can strengthen magnetic fields. If the black hole spins, magnetic structures may tap some of its rotational energy. Yet not every rapidly feeding black hole launches an obvious jet, showing that high fallback alone is not the entire explanation. Within the debris, magnetic fields influence angular momentum transport. Gas on an inner orbit moves faster than gas farther out. Magnetic field lines connecting different regions are stretched by this differential rotation. The resulting stress transfers angular momentum outward, allowing inner material to drift closer to the black hole, while outer material moves farther away. This process, often associated with the magnetorotational instability, is central to many accretion disk models. Without some method of moving angular momentum, gas would continue orbiting rather than falling inward. Turbulence generated by magnetic effects and shocks makes the flow highly variable. The accretion rate can rise and fall. Dense regions can temporarily block radiation. The inner disk may tilt or precess. Observed brightness can fluctuate over timescales ranging from minutes to months, depending on the size and location of the changing structure. These variations are not random annoyances in the data. They contain information about the scale of the emitting region and the motion of gas close to the black hole. If a brightness change occurs very rapidly, the source producing it cannot be extremely large. Light needs time to cross any emitting region. A flare that varies significantly over a few minutes must come from a region no wider than a few light minutes, unless relativistic motion alters the appearance. Astronomers use this simple light travel argument to place limits on the size of TDE emission zones. Fast X-ray variability often points toward activity close to the black hole, while slowly changing optical emission may arise in a more extended region. The debris may also form a warped disk. If its orbital plane is tilted relative to the black hole's spin, frame dragging affects inner and outer regions differently. The disk can twist, precess, or partially tear into separate rings. Internal pressure and viscosity resist these changes, trying to keep neighbouring sections connected. The outcome depends on the disk thickness, accretion rate, magnetic field, and spin of the black hole. A precessing inner flow or jet could cause quasi-periodic variations as its orientation changes relative to Earth. Clumps in the original stream add further irregularity. Self-gravity may preserve dense knots while the stream expands. If those knots return separately, they could create bursts in the fallback supply. The collisions between streams may also produce dense clouds that orbit for a time before dissolving. From far away, such structures could change spectral lines or temporarily obscure the centre. The debris is not obliged to behave like a smooth fluid simply because our simplest equations prefer it that way. Despite these complications, the overall direction of the process is clear. The stellar stream begins on highly elongated orbits. Intersections and shocks remove orbital energy. Gas spreads into a broader flow. Angular momentum is redistributed. Some matter moves inward, some moves outward, and some escapes in winds or jets. Radiation carries energy away. Over time, the remaining bound debris becomes more circularized, and the supply of new material declines. The declining fallback rate gradually changes the accretion flow. Early in the event, the black hole may receive matter at a rate above the Eddington limit, the point where outward radiation pressure becomes important enough to oppose continued inflow in a simple spherical picture. Accretion can still occur above this rate, but the flow becomes thick and inefficient at releasing all its energy as radiation. Winds carry away excess material and energy. Later, as the fallback rate decreases, the flow may become thinner, more stable, and better able to radiate from the inner disk. The black hole gains only part of the disrupted star. Some debris escaped during the original encounter. Some bound material is expelled during circularization or accretion. Some may remain orbiting for a long time. The portion that crosses the event horizon adds slightly to the black hole's mass and angular momentum, but for a supermassive black hole, one star is a very small contribution. The surrounding galaxy notices the flare far more than the black hole notices the increase in mass. Eventually, the returning stream becomes thinner because there is less material left on long orbits. Collisions weaken, winds subside, the accretion rate drops, and the bright central source fades. The black hole may return to the quiet state it occupied before the star arrived. A faint disk or lingering radio source can remain, but the dramatic phase is temporary. What began as a stable star has been divided among several destinations: gas escaping into the galaxy, matter orbiting in an extended flow, winds moving away from the center, and material crossing the event horizon. That competition with the light of an entire galaxy begins when the returning debris finally finds an efficient way to release the energy stored in its motion. The stellar gas has already travelled deep into the black hole's gravitational field, accelerated to extraordinary speeds, and wrapped itself into intersecting streams. Until those streams collide or begin moving inward through an accretion flow, much of that energy remains locked in organised orbital motion. Once shocks, turbulence, and magnetic stresses disrupt that organisation, the gas heats rapidly. Radiation begins escaping from the region around the black hole, and a galactic centre that may have appeared quiet for decades of observations can brighten into a new point of light. The black hole is not producing this radiation from inside its event horizon. Nothing that has crossed that boundary can return and announce what happened. The flare comes from material that is still outside, sometimes many times farther from the black hole than the horizon itself. Gas collides, compresses, circulates, and falls onto smaller orbits. Each inward step releases part of its gravitational energy. Some of that energy becomes heat within the debris. Some accelerates winds or particles. Some is carried away as visible light, ultraviolet radiation, X-rays, radio waves, and, in rare jetted events, even higher energy emission. A TDE can therefore shine across much of the electromagnetic spectrum rather than appearing in only one kind of telescope. The phrase outshine an entire galaxy may sound like an enthusiastic exaggeration created for a poster, but the basic comparison can be real. A normal galaxy contains billions of stars whose combined light is spread over a region tens of thousands of light-years wide. A tidal disruption flare concentrates an immense power output into a region around one central black hole. Near its peak, the new source can rival or temporarily exceed much of the visible or ultraviolet light from its host galaxy. From a sufficiently large distance, astronomers may see the central point brighten dramatically, while the rest of the galaxy remains almost unchanged. This does not mean the flare contains more total energy than every star in the galaxy will produce during its lifetime. The important difference is power, meaning energy released per unit of time. A galaxy shines steadily for billions of years. A tidal disruption event converts a fraction of one star's mass and orbital energy into radiation over months or years. The brief release can be extraordinarily intense even though the available fuel is limited. A camera flash can momentarily appear brighter than a lamp that remains switched on all evening, but the lamp may still release more energy overall. The TDE is the cosmic version of that short, powerful release, except the flash may remain bright long enough for astronomers to follow it through several observing seasons. Accretion around black holes is particularly effective at releasing energy because matter can move very deeply into a gravitational field before disappearing across the event horizon. In an ordinary star, nuclear fusion converts a small fraction of the fuel's mass into energy. Material orbiting a black hole can, under suitable conditions, release a considerably larger fraction of its rest mass energy before crossing the horizon. The exact efficiency depends on the black hole's spin, the structure of the accretion flow, and how close the gas can orbit while remaining temporarily stable. Before that fading stage arrives, however, the conversion of orbital energy into radiation can make the galactic nucleus brighten with extraordinary speed. A region that previously appeared inactive may suddenly become a strong source of ultraviolet light, visible light, and X-rays. The debris wrapping around the black hole does more than feed it. It creates a temporary engine in which gravity powers one of the brightest short-lived flares a galaxy can display. And the next question is how that flare can become luminous enough to compete with the combined light of billions of ordinary stars. Not all of the stellar debris contributes equally. A large fraction escape during the original disruption, or is later driven away in winds. Some gas remains on wide orbits, and returns only after a long delay. Even so, the amount reaching the central region can be enough to create a brilliant transient source. A star contains an enormous reservoir of matter. Converting even a small portion of that reservoir into radiation, with the efficiency available near a black hole, can illuminate a galaxy's nucleus very effectively. It is rather inconvenient for the star, but extremely helpful for telescopes. The first light may be produced before a stable accretion disk has formed. When returning debris streams strike one another, their collision shocks can generate heat at distances well outside the innermost orbits. Some researchers argue that these stream collisions may power a substantial part of the visible and ultraviolet emission in many TDEs. Other models place the main energy source closer to the black hole, with radiation from the accretion flow absorbed and re-emitted by debris farther out. Both mechanisms may operate, and their relative importance can change from one event to another. Reviews of TDE emission models distinguish between rapidly circularized events, dominated by disk accretion, and events where shocked streams can radiate strongly before a compact disk is fully established. This helps explain one of the long-standing puzzles of tidal disruption astronomy. Early theoretical pictures often expected the flare to be strongest in X-rays, because material near the black hole should become extremely hot. Yet many events discovered by optical surveys shined most clearly in visible and ultraviolet light. Their observed temperatures are hot by ordinary stellar standards, often producing a blue appearance, but they are cooler than the innermost X-ray emitting gas expected near an accreting black hole. Something must either create the optical light farther out, or transform the hidden high-energy radiation before it reaches us. Reprocessing offers one explanation. Imagine that a hot inner accretion flow produces mostly extreme ultraviolet and X-ray photons. Around it sits a thick expanding layer of stellar debris. High-energy photons enter that material and are absorbed by atoms and ions. Their energy is shared through the gas and later emitted again as lower-energy ultraviolet or visible photons. The surrounding debris effectively changes the colour of the original radiation. From Earth, astronomers see a large, warm-looking source, even though the primary engine may be much smaller and hotter. The comparison to a lampshade is often useful, as long as we allow the lampshade to be made of plasma, expanding at thousands of kilometres per second, and thoroughly unsuitable for the average bedside table. The inner source supplies the energy. The surrounding material determines how that energy emerges. A dense envelope can hide direct X-rays while allowing reprocessed optical light to escape. If the envelope thins or becomes highly ionized, X-rays may later pass through, causing the event's observed colour and spectrum to change. Radiative transfer models show that an extended debris envelope can transform soft X-rays into strong optical emission and can also affect the relative strengths of hydrogen and helium spectral lines. Another possibility is that the visible light is generated directly in shocks where the debris streams collide. These intersections can occur much farther from the black hole than the inner edge of an accretion disk. A larger emitting region naturally has a lower temperature if its energy is spread over more surface area. The gas can still become hot enough to glow strongly in ultraviolet and blue visible wavelengths without reaching the temperatures required for bright X-ray emission. In this picture, the optical flare traces the circularization process rather than the final accretion of gas near the event horizon. Both pictures may be correct under different circumstances. A deep encounter can cause strong relativistic precession, forcing streams to collide close to the black hole and dissipate energy efficiently. Another event may produce weaker intersections farther away, allowing a broad eccentric flow to remain for many orbits. The mass and spin of the black hole, the structure of the star, the depth of the passage, and the viewing direction can all influence which region dominates the observed flare. As a result, TDEs are a family rather than a set of identical explosions. Some are bright in optical and ultraviolet light but weak in X-rays. Some produce strong soft X-ray emission. Others change from one state to another as the debris evolves. A few launch relativistic jets and become extremely luminous in X-rays and gamma rays. Radio emission may appear early, late, or not at all. The star is disrupted by the same basic tidal mechanism, but the visible aftermath depends on how the debris processes and releases energy. The optical and ultraviolet light often rises over days or weeks. At first, the central point in the host galaxy may be too faint to attract attention. It grows steadily brighter as more material returns, shocks strengthen, and the emitting region develops. The flare reaches a peak and then begins fading as the supply of returning debris declines. The exact rise and decline vary. Simple models predict a particular long-term fall in the fallback rate, but observed brightness does not always follow that law perfectly, because radiation is filtered through the changing accretion flow, winds, and debris envelope. One especially interesting feature is that the optical colour of many TDEs remains fairly stable while the source fades. An ordinary cooling explosion might become noticeably redder as it expands and loses heat. TDEs can maintain high temperatures for a long time, suggesting that continuing energy from fallback, shocks, or accretion keeps the emitting gas hot. The apparent size of the optical photosphere, the region from which light escapes effectively, may shrink as the event fades, while the temperature changes less dramatically. The photosphere does not have to be a solid surface. It marks the approximate layer where the debris becomes transparent enough for photons to escape. Below it, light is repeatedly absorbed and scattered. Above it, radiation can travel outward more freely. As the gas expands and its density decreases, the photosphere moves through the debris. What astronomers measure as the apparent radius and temperature of the flare can therefore evolve even if the central engine behaves differently. Spectroscopy provides a more detailed view. When astronomers separate the light into its component wavelengths, they often find broad emission lines from hydrogen, helium, and sometimes highly ionized nitrogen or oxygen. The broadness indicates gas moving at high speed. Some TDEs show mainly hydrogen features. Others have strong helium. A third group displays a combination of hydrogen, helium, and fluorescence lines, created when intense ultraviolet radiation excites surrounding ions. These spectral classes tell researchers about the temperature, density, ionization state, and geometry of the debris, although they don't always reveal the original star's composition as directly as one might hope. A weak hydrogen line, for instance, does not necessarily mean the black hole disrupted a hydrogen-poor star. Hydrogen may still be present but hidden by optical depth effects, or kept in an ionization state that does not produce the expected line efficiently. The flare's radiation can transform the debris so thoroughly that identifying the star becomes rather like determining the ingredients of a meal after someone has heated it to several tens of thousands of degrees and fired part of it into space. X-rays offer a view closer to the black hole. Gas in the inner accretion flow can reach temperatures of hundreds of thousands or millions of degrees, producing high-energy photons. Many TDEs emit relatively soft X-rays, meaning their X-ray spectrum is weighted toward the lower energy part of the X-ray band. These photons may come from the hot inner disk or from a compact region called a corona, where energetic electrons increase the energy of lower frequency photons through repeated scattering. The corona is familiar from persistently active black holes, but a TDE gives astronomers an opportunity to watch such a structure appear around a black hole that may have been quiet beforehand. Observations of AT2021 for example, followed changes across ultraviolet and X-ray wavelengths as a new accretion flow formed around a black hole of roughly 10 million solar masses. NASA described the event as an unusually close look at the development of structures around a newly feeding black hole. X-ray brightness can vary rapidly because the emitting region is compact. A noticeable change over minutes or hours suggests that at least part of the source lies close to the black hole, since a much larger region could not coordinate its brightness faster than light can cross it. Some TDEs show fluctuations or quasi-periodic signals that may be connected to motion near the innermost stable orbits. Such behavior can potentially reveal the black hole's mass and spin, although interpreting the signal requires care because several physical mechanisms can produce variability. The contrast between optical and X-ray emission can change over time. An event may begin with strong visible and ultraviolet light, while X-rays remain weak. Months later, X-rays can brighten as the surrounding debris becomes less opaque, or as the inner accretion flow changes. The reverse can happen as well. A bright X-ray source may fade suddenly if the inner disk cools, if material temporarily blocks our view, or if the accretion state reorganizes. A useful way to understand this is to imagine several nested regions. Closest to the black hole lies the hottest gas, where X-rays may be produced. Farther out, eccentric debris streams collide and generate shocks. Beyond them, winds and reprocessing layers absorb and redistribute radiation. Still farther away, outflowing material interacts with the gas of the galactic center and produces radio waves. Telescopes observing different wavelengths are therefore not simply seeing the same object in different colors. They may be studying different physical zones, each evolving on its own timescale. Radio emission is generally produced when fast material from the event collides with the surrounding environment. The collision drives a shock through the gas. Electrons are accelerated to high energies and spiral around magnetic field lines, releasing synchrotron radiation. Unlike the optical flare, which can become bright relatively early, radio emission may strengthen later as an outflow travels far enough to sweep up surrounding matter. Radio observations help estimate the speed and total energy of the expelled material. Even an event without a narrow jet can drive a broad wind. During the early phase, the fallback rate may exceed the amount that can be steadily accreted while allowing radiation to escape efficiently. Pressure builds, and part of the inflowing material is pushed outward. The wind can carry a large fraction of the star away from the black hole, which means the returning debris does not all become part of the black hole. It arrives at the center only to be redirected again, a journey that might feel unnecessarily complicated if gas were capable of filling out a complaint form. In rare cases, the outflow becomes a relativistic jet. These narrow beams can travel close to the speed of light and produce intense X-ray, gamma ray and radio emission. Swift J1644+57, discovered in 2011, became the best-known example of a likely jetted tidal disruption event. Its powerful high-energy flare and rapid variability suggested that a newly formed jet was aimed roughly toward Earth. relativistic beaming made the source appear far brighter than it would from another direction. Reviews of TDE observations identify Swift J, 1644+57, and a small number of similar events as a distinct rare jetted population. The jet does not emerge from inside the event horizon. It is launched by processes in the magnetized gas immediately outside the black hole, potentially drawing energy from the accretion flow and the black hole's rotation. Magnetic field lines can guide plasma along the rotation axis, producing two oppositely directed beams. We normally detect the beam pointed toward us much more strongly, because relativistic motion concentrates its radiation into the forward direction. This produces a major selection effect. Many TDEs could launch weak or moderately powerful jets that do not point toward Earth. Their high energy emission would be far less obvious. Radio observations made later may still reveal an off-axis outflow after it slows and spreads. Researchers continue searching for such hidden jets to determine how often TDEs produce them and what conditions are required. Whether a jet forms may depend on black hole spin, magnetic flux, the rate of accretion, and the orientation of the debris. A rapidly spinning black hole offers a large reservoir of rotational energy, but spin alone may not be enough. The accretion flow must also accumulate and organize a strong magnetic field. The disrupted star supplies some magnetic field, though it is uncertain how quickly that field can be amplified and arranged on the necessary scale. For most TDEs, the more familiar flare remains thermal optical, ultraviolet or X-ray emission, rather than a powerful jet. The event can still be extremely luminous. The black hole does not need to produce a narrow beam to make itself known. A hot debris envelope radiating in many directions can already transform the center of its host galaxy into one of the brightest points in the sky at that distance. Dust around the galactic nucleus may add a delayed infrared signal. Ultraviolet and visible light from the flare travels outward and strikes dust grains located light months or light years from the black hole. The grains absorb the radiation, heat up, and re-emit energy in infrared wavelengths. Because the light must travel to the dust, and then onward to Earth, the infrared response arrives later than the original flare. This is called a dust echo. The delay acts as a measuring tool. By tracking when the infrared emission rises, astronomers can estimate the distance between the black hole and the surrounding dust. The strength of the echo reveals how much radiation the flare produced and how the dust is distributed. Even after the central optical source begins fading, the dust can continue repeating the news outward, much as a distant wall returns an echo after the original sound has stopped, except in this case the message is carried by heat rather than air. A similar delay can appear between different electromagnetic bands if radiation must travel through or be processed by separate regions. Ultraviolet changes may precede optical changes. X-rays may rise before or after visible light. Radio emission can emerge much later. By comparing these timings, astronomers map the TDE without resolving it directly. The event is far too small and distant to photograph in detail, but light travel delays reveal the approximate arrangement of its components. The total brightness is not determined only by how much mass returns. There is an upper scale known as the Eddington luminosity, where outward pressure from radiation becomes comparable to inward gravity for ionized gas in a simple, steady system. If the flare tries to radiate far above this level, photons push strongly against the incoming material. That does not impose an unbreakable brightness ceiling. Real accretion flows are not perfectly spherical. Radiation can escape more easily in some directions, and matter can continue inward, while winds carry excess energy and mass outward. Still, the Eddington scale helps researchers understand why early TDE accretion may become thick, windy, and radiatively complicated. For a lower mass central black hole, the returning stellar debris can exceed the Eddington accretion rate by a large factor. The early flow may then trap some radiation within the gas. Rather than escaping immediately, photons are carried inward or outward with the moving material. Much of the supplied energy goes into driving a wind. Later, As the fallback rate declines, the flow becomes less extreme and may settle into a thinner disk that radiates more predictably. Around a more massive black hole, the same stellar supply may remain closer to or below the Eddington rate. The disk can behave differently, producing another source of diversity among TDEs. Black hole mass therefore affects not only whether a star is disrupted outside the horizon, but also the character of the flare that follows. The rise to maximum brightness does not necessarily occur when the fallback rate reaches its peak. If circularization is slow, gas may return without releasing its energy efficiently. The brightest emission could be delayed until streams collide strongly, or an accretion flow develops. If reprocessing material is initially too dense, radiation may need time to diffuse outward. The visible peak is therefore a result of both energy production and the ability of photons to escape. After the peak, the source generally fades, but the decline can contain interruptions. Brightness may level into a plateau, drop abruptly, or rise again. A delayed X-ray component may emerge. Radio emission may strengthen. Spectral lines can change as the density and ionization of the debris evolve. These variations show that the fading flare is not simply a light bulb being slowly dimmed. It is a changing physical system whose streams, disk, winds, and surrounding gas continue influencing one another. Some TDEs remain detectable in X-rays for years. NASA observations have described long-lasting X-ray sources associated with stellar disruption, including events whose feeding continued much longer than early simple estimates expected. A prolonged flare may indicate a massive star, slow circularization, unusual accretion physics, or a supply of debris returning over an extended period. Eventually, the fallback rate becomes small, the wind weakens, the reprocessing envelope thins, and the optical flare fades into the background light of the galaxy. The inner disk may continue producing faint ultraviolet or X-ray emission, after ordinary optical surveys can no longer separate it easily from the host. Radio waves from the expanding outflow can persist even farther into the future. The black hole gradually returns to its earlier quiet state, now slightly more massive and surrounded by the scattered remains of the star. For someone looking at a telescope image, none of this complexity appears as a detailed spiral of gas. The event is usually an unresolved point near the center of a distant galaxy. Its changing brightness and spectrum are the evidence. Astronomers may first see one blue-white point that was absent in older images. They then gather observations at many wavelengths and over many months, trying to decide whether the flare came from a tidal disruption, a supernova, ordinary black hole activity, or something less familiar. That identification is not automatic. Galaxies contain several kinds of objects capable of changing brightness. Active galactic nuclei flicker as their accretion flows vary. Supernovae can occur near galactic centers. Compact objects can produce high-energy transients. Even unusual stellar explosions may imitate parts of a TDE light curve. The event's central position, persistent high temperature, spectral lines, X-ray behavior, and gradual fading all provide clues, but no single feature solves every case. By the time the flare reaches Earth, the star may have been gone for hundreds of millions of years. Its debris may already have dispersed and the black hole may already be quiet again. The light arriving at our telescopes is a delayed record of the energy release, separated into visible ultraviolet, X-ray, infrared, and radio messages. Finding the flare is only the first step. Astronomers must then combine those messages and determine whether they are truly watching the final light of a star that passed too close to a black hole. Detecting the final destruction of a star begins with a comparison. Astronomers look at one image of the sky, then another image taken later, and ask a simple question: what has changed? Most of the stars remain where they were. Galaxies keep their familiar shapes. The background sky looks almost identical. Then a new point of light appears near the center of a distant galaxy where no such bright source was visible before. It may be faint at first, no more than a small increase in brightness among billions of other objects. Over the following nights, however, it grows stronger. The centre of the galaxy becomes bluer and brighter, and automated systems begin raising alerts. Somewhere inside that distant galaxy, something has released an enormous amount of energy. The difficult part is deciding what. Astronomers do not usually see the star itself before the disruption. The host galaxy may be hundreds of millions or billions of light years away, and the individual star was far too faint to separate from the combined glow of the galaxy. No telescope records a neat image of the star approaching the black hole, stretching into a stream and wrapping around the centre. Instead, scientists discover the aftermath. They receive the light after the star has already been pulled apart, and they reconstruct the event from its position, brightness, colour, spectrum, and behaviour over time. This makes tidal disruption astronomy a form of distant investigation. There is no surviving star to examine. The black hole remains invisible. The debris is too small on the sky to resolve directly. Astronomers must gather clues from photons that left the galactic centre long ago. Every observation answers one question and usually introduces two more, which is a very efficient way to maintain employment in astrophysics. The first clue is often the location of the flare. Massive black holes are expected to reside near the centres of most large galaxies. A transient source appearing far out in a galactic disk is more likely to be an exploding star, although unusual events can occur almost anywhere. A flare positioned extremely close to the nucleus immediately becomes more interesting. It could represent a tidal disruption, but it might also be ordinary variability from an active galactic nucleus, where the black hole has already been feeding on surrounding gas. Position therefore helps, but it cannot settle the case alone. Astronomers need to determine how close the source lies to the true centre of the host galaxy. This requires careful measurements known as astrometry. Images from different nights must be aligned. The brightness distribution of the galaxy must be modelled. Atmospheric blurring, telescope motion, detector effects, and the galaxy's own uneven structure must all be considered. A small apparent offset can result from measurement uncertainty rather than a real physical separation. When the flare is found at the nucleus within the limits of the observations, the tidal disruption interpretation becomes more plausible. The source is appearing exactly where a central massive black hole should be. Yet the investigators still have plenty of work ahead. Galactic nuclei are busy places, and black holes can vary for several reasons. Gas clouds can move through an existing accretion disk. The feeding rate can change. Dust can temporarily obscure or reveal the central engine. Some active galactic nuclei brighten dramatically after years of quiet behaviour. A central flare is therefore a promising clue rather than a signed confession. Modern searches rely on wide-field surveys that repeatedly photograph large areas of the sky. Instead of choosing one galaxy and waiting patiently for a star to be destroyed, which could require a very generous amount of patience, astronomers monitor millions of galaxies at once. Automated telescopes revisit the same fields every few nights, or sometimes more frequently. Computers subtract an older reference image from a new one. Anything unchanged disappears from the difference image, while new or varying sources remain. Image subtraction is one of the quiet technical achievements behind transient astronomy. A new image rarely matches the old one perfectly. The atmosphere may have blurred the stars differently. The telescope may have been pointed a fraction of a pixel away from the previous position. The background brightness may have changed because of moonlight, air glow, or thin clouds. Software adjusts the scale, alignment, and point spread function before subtracting the images. When it works well, a galaxy that normally fills many pixels vanishes from the comparison, leaving a small bright spot at its centre. The initial alert may contain very little information. It records the position, brightness, time, and perhaps a few measurements in different filters. Thousands or even millions of alerts can be generated during a large survey night. Most do not represent tidal disruption events. Some are variable stars in our own galaxy. Others are asteroids passing through the field. Many are supernovae. Some are artifacts created by detector defects, cosmic rays, satellite trails, or imperfect subtraction. Automated classifiers and human observers must decide which candidates deserve immediate follow-up. Speed matters because the rise of the flare contains valuable information. A TDE discovered near maximum brightness is useful, but one found during its earlier stages is even better. Astronomers can measure how quickly the light increases, whether the colour changes, and whether X-rays or radio waves appear before or after the optical peak. Those early observations help distinguish between models in which stream collisions power the visible emission, and models in which a central accretion flow produces high-energy radiation that is reprocessed farther out. Once a promising central flare is identified, astronomers request observations from other telescopes. This can involve a network of facilities spread across the world and above it. One telescope measures visible light through several filters. Another obtains a spectrum. A space-based observatory checks the ultraviolet or X-ray emission. Radio telescopes search for an outflow. Infrared instruments look for heated dust. The original survey may have found only a new point of light, but follow-up observations begin building a physical picture. Brightness measurements taken over time form a light curve. The horizontal direction represents time, while the vertical direction records how luminous the source appears. A TDE light curve often shows a rise toward a peak, followed by a slower decline. The broad shape is related to the return of stellar debris, the formation of an accretion flow, and the changing ability of radiation to escape. However, there is no single curve that every TDE follows exactly. The simplest theoretical model predicts that the fallback rate of debris eventually decreases according to a particular power law. In that idealized picture, the brightness might fade in a similarly organized way. Real observations are more varied. Some events decline smoothly. Others remain near maximum brightness for a while. A few fade and brighten again. X-ray and optical light curves may follow different patterns. Delayed circularization, winds, obscuration, dischanges, and reprocessing can all modify what the telescopes see. This means astronomers should not identify a TDE simply because its brightness declines at roughly the expected rate. The light curve is part of the evidence, not a universal fingerprint. A supernova can also rise and fade over weeks or months. An active galactic nucleus can brighten and decline. Several unusual transients produce curves that overlap with the broad behavior of tidal disruptions. Reliable classification requires several clues pointing in the same direction. Color provides another. Many optical TDEs appear unusually blue, indicating a high temperature. Astronomers measure the brightness through different filters, perhaps one weighted toward blue light and another toward red. By comparing those measurements, they estimate the shape of the source's thermal emission and infer an approximate temperature. TDE optical temperatures often remain high for months, while the overall luminosity falls. That persistent blue color can help separate a tidal disruption from many ordinary supernova. Expanding supernova debris generally cools and becomes redder as time passes, although there are important exceptions. In a TDE, continuing energy from shocks, fallback, and accretion can keep the emitting region hot. The apparent temperature may stay relatively stable while the effective photosphere shrinks. To observers, it is as though the source remains the same color while becoming smaller and dimmer. The word photosphere here does not refer to the surface of a surviving star. It is the region within the debris or outflow where photons can finally escape without being repeatedly absorbed and scattered. The location of this boundary changes as the gas expands and thins. Astronomers combine the measured temperature and luminosity to estimate an effective radius for the emitting region. That radius is often much larger than the innermost part of the accretion disk, which supports the idea that optical light is produced or reprocessed well outside the event horizon. A spectrum offers far more detail than color alone. Instead of measuring light through a few broad filters, a spectrograph separates it into thousands of narrow wavelength channels. Atoms and ions absorb or emit light at particular wavelengths, leaving identifiable patterns. These spectral lines reveal what elements are present, how ionized the gas is, and how quickly it is moving. Many TDE spectra contain broad emission lines associated with hydrogen and helium. Broad means that the line is spread over a wide range of wavelengths, because the gas has a large range of velocities. Some debris is moving toward Earth, shifting its light slightly toward the blue. Other debris is moving away, shifting its light toward the red. Material travelling across our line of sight contributes between those extremes. The combined result can indicate speeds of thousands or tens of thousands of kilometers per second. The exact line shapes vary. Some events show strong hydrogen emission, others are dominated by helium. A few display features associated with highly ionized nitrogen, oxygen, or iron. These differences once encouraged the idea that helium-dominated TDEs might come from stars that had lost their hydrogen envelopes. That may happen in some cases, but the interpretation is not always so direct. Radiation moving through dense gas can suppress one line and strengthen another. The same chemical mixture can produce different spectra under different temperatures, densities, and ionization conditions. Astronomers therefore treat the spectrum as evidence about the debris environment, rather than a simple list of the destroyed star's ingredients. To understand it, they model how radiation interacts with the gas. They calculate which ions should exist at a given temperature, how frequently photons are scattered, and where each line might form. A strong helium line may reveal the ionizing radiation field as much as it reveals the original stellar composition. Certain spectral features can be excited through fluorescence. High-energy photons are absorbed by ions, raising their electrons into energetic states. The ions then release photons at other wavelengths as the electrons step back down. This can produce unusual combinations of lines, particularly in the dense and strongly illuminated environment around a TDE. Such features help astronomers estimate the hidden extreme ultraviolet radiation that may be difficult to observe directly. Earth's atmosphere blocks most ultraviolet and X-ray radiation, so space telescopes are essential. Ultraviolet observations are especially valuable because TDEs often radiate strongly at wavelengths shorter than visible light. A source that seems moderately bright in an optical image may release much more energy in the ultraviolet. Measuring that part of the spectrum gives a better estimate of the temperature and total luminosity. Ultraviolet observations can also follow the event after the visible light begins blending into the host galaxy. Old stars in many galactic centres emit relatively little far ultraviolet light, so a hot transient can stand out clearly. The ultraviolet brightness may remain detectable for months or years, revealing continued accretion or reprocessing long after the initial peak. X-rays provide a different view. They often originate closer to the black hole, where the gas reaches much higher temperatures. A strong, soft X-ray source appearing at the centre of a previously quiet galaxy is an important TDE clue. Soft in this context means that the photons lie toward the lower energy end of the X-ray range, though they are still considerably more energetic than visible light. The spectrum can resemble thermal emission from a hot accretion disk. Not every tidal disruption is bright in X-rays. Some optically selected events show very weak X-ray emission. This could mean that a compact disk has not yet formed, that the accretion flow is intrinsically faint in X-rays, or that thick debris is absorbing the inner radiation. Astronomers may continue monitoring these sources because X-rays can appear later as the surrounding material becomes transparent. A delayed X-ray rise can be particularly informative. Suppose an optical flare peaks while the X-ray source remains hidden. Months later, the X-rays increase without a second major optical outburst. One interpretation is that the hot inner disk existed earlier, but was concealed by gas. As the debris expanded and thinned, the line of sight cleared. Another possibility is that circularization was slow, and a compact accretion flow developed only after a delay. Distinguishing between these ideas requires detailed timing and spectral analysis. Rapid X-ray variability gives clues about the size of the emitting region. If the brightness changes significantly within an hour, the region responsible cannot be much larger than 1 light hour unless relativistic effects are involved. A very compact source points toward the innermost part of the accretion flow. Optical emission usually changes more slowly because it is produced over a larger region. Occasionally, astronomers detect repeating or nearly periodic X-ray signals. These may result from material orbiting close to the black hole, a surviving stellar core returning repeatedly, changes in a precessing disk, or interactions involving another compact object. Such signals are exciting because orbital periods near the black hole can reveal its mass and perhaps its spin. They are also difficult to interpret since several mechanisms can generate repeated variability. Radio telescopes search for signs that the disruption launched material outward. Radio emission is usually not produced directly by the hot thermal surface that creates the optical flare. It often comes from high-energy electrons spiraling around magnetic fields after an outflow collides with gas surrounding the galactic center. The process is known as synchrotron emission. The radio signal can appear long after the optical discovery. An outflow must travel outward before it sweeps up enough surrounding material to create a strong shock. The delay, brightness, and spectrum allow astronomers to estimate the outflow's speed, energy, and density. A slowly expanding wind produces one kind of radio evolution. A relativistic jet produces another. Jetted tidal disruptions can announce themselves through exceptionally bright and rapidly variable X-ray or gamma-ray emission. When a relativistic jet points toward Earth, its radiation is concentrated in our direction. These events can be detected across enormous distances. Their light curves may change violently. Unlike the smoother thermal emission of many ordinary TDEs, radio follow-up can trace the jet as it interacts with the surrounding gas and gradually slows. The rarity of obvious jetted events does not necessarily mean jets are almost never produced. A narrow jet is easy to detect only when it points reasonably close to us. Most jets, if they exist, would be aimed elsewhere. Astronomers search for off-axis jets through late-time radio emission that becomes less tightly beamed as the outflow decelerates. A radio signal appearing months or years after an apparently normal optical TDE may reveal hidden energetic activity. Infrared telescopes provide yet another layer of evidence. Light from the flare travels outward and heats dust surrounding the galactic nucleus. The dust re-emits that energy in infrared wavelengths, creating a delayed echo. The time between the optical flare and the infrared response indicates roughly how far the dust lies from the black hole. This dust echo can confirm that the central flare produced strong ultraviolet radiation, even when that radiation was not observed directly. Dust grains are effective at absorbing ultraviolet and visible photons. Their later warmth records the energy that reached them. In some cases, an infrared survey may discover the echo even when the original event was hidden by dust along our line of sight. Neutrinos have also become part of the broader discussion around some candidate tidal disruptions. These nearly massless particles interact so weakly that they can travel through dense matter and across the universe with little disturbance. A few high-energy neutrino detections have been examined for possible associations with TDE-like flares. The evidence is still limited and interpretations remain debated, but such events may be capable of accelerating particles to extreme energies under certain conditions. Gravitational waves from an ordinary main-sequence star disrupted by a distant supermassive black hole are generally too weak for present detectors, especially compared with black hole or neutron star mergers. More compact encounters, such as a white dwarf interacting with an intermediate mass black hole, could create stronger signals at different frequencies. Future gravitational wave observatories may add another way to study some forms of tidal disruption, combining space-time vibrations with electromagnetic light. Even with observations across the spectrum, classification can remain uncertain. Astronomers compare the candidate with several alternative explanations. A supernova near the galactic nucleus is one possibility. Supernovae often produce spectral lines that evolve as the ejecta expand and cool. Their light curves may be powered by radioactive decay, shock interaction, or a compact remnant. The temperature commonly changes more dramatically than in a TDE, and the source may be slightly offset from the exact centre. An active galactic nucleus creates a more difficult comparison because it is already centred on the black hole. Astronomers inspect older observations to see whether the galaxy showed previous activity. Did the nucleus vary before the flare? Were narrow emission lines present in the host spectrum indicating long-term ionization by an active black hole? Was there persistent X-ray or radio emission? A galaxy with no clear history of activity provides a cleaner environment for identifying a TDE, though dormant-looking nuclei can still surprise everyone. Changing-look active galactic nuclei are particularly troublesome. These sources can brighten rapidly and develop or lose broad spectral lines as the accretion rate or obscuring material changes. Their transformation may resemble a tidal disruption. Long-term monitoring helps. An active nucleus may continue fluctuating after the initial flare, while a classical TDE should gradually decline as its limited debris supply is exhausted. The host galaxy itself offers statistical clues. TDS have been found more frequently than expected in a type of galaxy, with evidence of a recent burst of star formation that has since ended. These are often called post-starburst or E+A galaxies. Their spectra show a strong population of relatively young stars but little current star formation. The reason for the enhanced TDE rate is still being investigated. Such galaxies may have dense central stellar populations, unusual orbital structures, or black hole binaries left by mergers. Finding a candidate in one of these hosts raises its probability of being a TDE, but host type cannot serve as proof. Tidal disruptions also occur in other galaxies. Astronomers must avoid letting a statistical preference replace direct evidence. A blue central flare with broad helium lines in a post-starburst galaxy looks very promising, but it still deserves X-ray observations, continued photometry, and a careful comparison with alternatives. The black hole's likely mass is another important clue. Researchers estimate it using properties of the host galaxy, such as the velocity dispersion of stars in the central bulge or the bulge's total mass and brightness. If the inferred black hole is so massive that a sun-like star would probably cross the event horizon before being disrupted visibly, the ordinary TDE explanation becomes more complicated. Black hole spin, a giant star, or measurement uncertainty may still allow the event, but the mass estimate must be considered. The flare can sometimes improve the black hole measurement. The temperature of the inner disk, the timing of the fallback, rapid variability, and certain spectral features depend on black hole mass. By fitting physical models to the observations, astronomers estimate the mass independently of the host galaxy relationships. Agreement between several methods strengthens the interpretation. Polarization measurements can reveal the geometry of the emitting material. Light becomes polarized when it scatters through an asymmetric environment or is produced in an ordered magnetic field. A spherical envelope tends to yield little net polarization because different directions cancel. A flattened disk, elongated debris stream, or jet can produce a stronger signal. Changes in polarization over time may show the system becoming less obscured or more disk-like. High-resolution spectroscopy can track how emission lines shift and narrow. Early in the event, gas may be moving extremely fast and the lines can be broad. Later, as the debris settles or the emitting region moves outward, the profiles change. A line that appears displaced toward the blue may indicate that the approaching side of an outflow is more visible than the receding side. A double-peaked line might suggest rotating material, though radiative transfer effects can create similar shapes. No single telescope follows the entire event perfectly. Ground-based optical observatories lose sight of a galaxy when it moves too close to the Sun in the sky. Weather interrupts observations. Space telescopes have limited scheduling time. Some wavelengths are measured frequently, while others receive only a few snapshots. Astronomers piece together the available data, often combining instruments that were designed for very different purposes. Archival observations are extremely valuable. After a flare is discovered, researchers search older survey images to determine when it first began and whether the nucleus had varied before. An apparently new event may have been slowly rising below the detection threshold for weeks. A previous X-ray exposure may reveal that the black hole was already active years earlier. A radio map may show a persistent jet unrelated to the new flare. The past behavior of the galaxy can change the interpretation of the present event. Distance must also be measured so apparent brightness can be converted into true luminosity. Astronomers use the host galaxy's redshift, the stretching of its spectral features caused mainly by cosmic expansion, to estimate how far away it is. Once the distance is known, they calculate how much energy the flare actually emitted. A small point that looks modest in a telescope image may be producing more light than billions of suns. The redshift also changes the observed timing and wavelengths. Events in distant galaxies appear to evolve more slowly because cosmic expansion stretches the arrival times between photons. Their ultraviolet radiation may be shifted into visible wavelengths. Researchers correct for these effects before comparing one TDE with another. Without those corrections, a distant event might appear cooler and slower simply because the universe expanded while its light was travelling. Machine learning now helps sort the enormous stream of transient alerts. Algorithms are trained using known supernovae, variable stars, active galactic nuclei, TDEs, and instrumental artifacts. They compare colour, location, rise time, host galaxy, and previous variability. A promising TDE candidate receives a higher score and may be selected for follow-up. These systems are useful but not infallible. TDEs are rare and diverse, leaving fewer training examples than common supernovae. An algorithm may prefer familiar events and overlook something genuinely unusual. Human judgment remains important, particularly when deciding how to use scarce telescope time. The ideal candidate is interesting enough to investigate, but not so strange that no one knows which instrument to request, a balance the universe does not always respect. After months of observations, the evidence begins to form a consistent history. A blue flare appeared at the exact centre of a previously quiet galaxy. It rose over several weeks, maintained a high temperature, and developed broad hydrogen or helium lines. Ultraviolet emission remained strong. X-rays revealed hot material near the black hole, perhaps immediately or after a delay. The source faded as expected for a limited supply of returning debris. Radio observations showed a wind or jet moving into the surrounding gas. No previous long-term active nucleus was visible. At that point, astronomers can classify the source as a likely tidal disruption event. Likely remains an important word. Science rarely provides absolute certainty for a transient that happened hundreds of millions of years ago and cannot be repeated on request. Confidence comes from the agreement of independent clues. Position, colour, spectrum, temperature, timing, host properties, and multi-wavelength behaviour all support the same explanation. The observations then become more than a label. They are used to reconstruct the star's final passage. The rise time constrains the return of the most tightly bound debris. The peak luminosity estimates the energy release. Spectral lines reveal gas motion and ionization. X-rays probe the inner accretion flow. Radio waves measure outflows. Infrared echoes map surrounding dust. Late-time fading shows how the black hole's temporary supply diminishes. Each TDE adds another example to a growing population. By comparing many events, Astronomers look for patterns. Which black hole masses produce the brightest optical flares? Why do some events emit strong X-rays while others do not? How often are jets launched? Are certain stars disrupted more frequently? Why do some host galaxies produce so many candidates? How long does circularization usually take? The answers cannot come from one unusually well-observed event. They emerge statistically after surveys collect dozens, hundreds, and eventually many more examples. Yet even a large survey can miss entire groups. Dust may hide optical flares. X-ray instruments cover only part of the sky at a time. Short-lived events can rise and fade between observations. A disruption near a low-mass black hole may be faint, while one near a very massive black hole may disappear directly across the horizon. Jetted events are easiest to see when the beam points toward Earth. Every detection method has a bias, and astronomers must account for what their telescopes are less likely to find. This is why several kinds of surveys are needed. Optical searches discover blue central flares. X-ray surveys find hot accretion events that may be optically weak. Infrared observations reveal dust-hidden disruptions. Radio telescopes uncover powerful outflows. Together, they produce a broader census than any one wavelength could manage alone. Sometimes the evidence reveals that the star was not completely destroyed. The flare may repeat. A surviving object may remain on an orbit that brings it back toward the black hole. Instead of one smooth supply of debris followed by a gradual decline, astronomers may see separate episodes of brightening. The time between them can suggest an orbital period. Each return may remove another layer from the star, producing a series of partial disruptions. Such repeating sources complicate classification, because active galactic nuclei can also flare more than once. The recurrence must be examined carefully. Does the timing remain nearly regular? Do the spectra and temperatures resemble tidal debris? Does each flare weaken as the star loses mass or change because its structure is being altered? The damaged star now moves away from the black hole, but unlike the debris that has been completely separated from a fully destroyed star, part of its original structure remains intact. The dense central core has survived. Around it, the outer layers have been stripped, heated, stretched, and sent onto new orbits. Some of that lost gas remains bound to the black hole and will return to create a flare. Some may escape into the galactic center. The surviving core continues outward on an orbit that may eventually carry it back toward the same dangerous point. A partial tidal disruption is therefore not simply a weaker version of a complete disruption. It creates a different system altogether. A black hole with a temporary supply of debris, a damaged star whose internal balance has been changed, and an orbit that can turn one encounter into a repeating sequence. In the simplest description, the black hole has removed the star's outer envelope while leaving its denser interior gravitationally bound. Whether a star survives depends on how deeply it enters the tidal region and how its mass is arranged. A star is not equally dense from its surface to its center. Its outer gas is usually easier to remove, while the central region is held together more strongly. If the closest approach only grazes the tidal boundary, the black hole's differential gravity can peel material from the exterior without fully overcoming the self-gravity of the core. The result may look rather untidy, but it is physically understandable. The star loses mass where it is most weakly bound, while the material deeper inside remains connected. A more penetrating encounter can strip a much larger fraction, and a sufficiently deep passage leaves no surviving core at all. Simulations show that stellar type matters greatly. Centrally concentrated, higher mass or evolved stars can sometimes tolerate repeated small losses, whereas some lower mass stars become less stable after stripping and may be destroyed after only a few returns. Survival does not mean the star leaves unchanged. Removing the envelope alters the balance between gravity and pressure throughout what remains. The core may expand, contract, heat, cool, spin faster, or begin oscillating. Tidal forces deposit energy inside it, and the loss of material changes the pressure that once pressed down on deeper layers. the remnant must find a new equilibrium while it is racing away from the black hole. This adjustment can take much longer than the close passage itself. In some models, the surviving star becomes larger and less centrally concentrated, making it more vulnerable when it returns. In others, a compact remnant stays dense enough to endure many passages. The outcome depends on the original mass, age, rotation, chemical structure, and the fraction removed. The black hole has not merely trimmed the star, it has changed the object that will face the next encounter. Mass loss can also give the survivor a gravitational kick. Material is not always removed symmetrically from both sides. If more gas escapes in one direction than another, the remaining core recoils slightly, just as a boat shifts when someone steps off one side rather than the middle. This kick can change the star's orbital energy and angular momentum. It might become more tightly bound to the black hole, move onto a wider orbit, or in some cases receive enough energy to escape. The kick is not usually comparable to the tremendous speed of the close passage, but a small change can matter greatly on a highly elongated orbit. When the star returns years later, its closest approach may be slightly deeper or shallower than before. The interval between flares may change as well, giving astronomers a way to detect the accumulated effects of tidal heating and asymmetric stripping. A star that remains bound begins a long trip away from the black hole. Near pericenter it moved at enormous speed, but gravity gradually slows it as it climbs outward. At the distant end of the orbit it turns and begins falling back. The orbit can be extremely eccentric, meaning it is very stretched rather than nearly circular. The star may spend almost all of its time far from the black hole, and only a short interval passing through the dangerous tidal region. If its orbital period is a few months, a new flare might appear several times during an observing program. If the period is several years, astronomers must maintain records across changing instruments, research teams, and occasionally the retirement of a perfectly good laptop. Much longer periods are possible too, which means some apparently one-time TDEs may be partial disruptions whose next episode will not occur within a human career. During the next close passage, the remnant is not meeting the black hole for the first time. Its shape, spin, and internal density have already been modified. Tidal oscillations from the earlier encounter may not have fully faded. The core may be rotating more rapidly, because the black hole transferred angular momentum into it. If that rotation is aligned with the orbital motion, material at the surface can be easier to remove. Recent simulations indicate that stellar spin can help produce successive flares that become dimmer, because a rapidly rotating survivor may lose mass in a different pattern on each return. Other stars behave in the opposite manner. After losing outer material, they expand or become less concentrated, so the next passage removes even more mass and creates a brighter flare. Repeated disruptions are therefore not expected to behave like a photocopier producing identical pages. The star changes after every visit. Each new stripping episode produces another debris stream. Some material falls back and powers a fresh outburst, while the star continues along its orbit once again. The flare may resemble the previous one in timing, temperature, and spectrum, especially if the amount of removed mass and the path through the tidal region remains similar. Alternatively, it may brighten faster, peak at a different luminosity, show stronger X-rays, or disappear more abruptly. The delay between the star's pericenter passage and the observed flare also need not remain constant. Debris must still return, collide, circularize, and begin releasing energy. A change in stream geometry or accretion efficiency can shift the visible outburst even if the stellar orbit itself remains regular. This is why a repeating light curve can reveal an orbital clock without every flare being a perfect match. One of the best-known repeating nuclear transients is AS SN-14KO, located at the center of the active galaxy ESO 253-G003. Its outbursts recur roughly every 114 days, and by early 2026 more than 30 flares had been reported. The events are remarkably regular, although the recurrence interval has slowly changed. A leading explanation is that a star on a tightly bound eccentric orbit loses a small amount of material during each close approach. Models suggest that a relatively massive, evolved and centrally concentrated star could survive many such encounters while shedding a few hundredths of a solar mass at a time. The system is not a perfectly settled case, because it lies in an already active galactic nucleus where other kinds of repeating accretion behavior are possible, but its regularity makes repeated tidal stripping a compelling interpretation. How did a star enter such a short, dangerous orbit? One possibility begins with a binary star system. If a close pair approaches a supermassive black hole, the black hole can tear the pair apart. One star may be ejected at high speed, while the other loses orbital energy and becomes trapped around the black hole. This Hill's mechanism can naturally place the captured star on a highly eccentric orbit, with a pericenter near the tidal radius. Calculations show that it can produce an orbital period similar to the roughly 114-day cycle of ASA SSN-14KO. The captured star then returns repeatedly, losing material each time. From the star's perspective, being the member that remains behind is not the favourable half of the arrangement, though the ejected companion may also find itself leaving the galaxy without much time to pack. A T2018FYK offers a different and more puzzling pattern. It initially behaved like a bright TDE, then its X-ray and ultraviolet emission dropped dramatically around 500 to 600 days after discovery. The source later brightened again, and a second sharp decline began in August 2023. Under the repeating partial disruption interpretation, a surviving star follows an orbit of about 1,306 days, returning to pericenter and interrupting or renewing the debris supply in a repeating cycle. That explanation successfully predicted the second shutoff, which strengthened the case for a stellar survivor. Yet another study has proposed that a pair of massive black holes could interrupt the debris flow from a one-time disruption and create some of the same unusual changes. A T2018FYK is therefore a useful reminder that an unusual light curve can support more than one physically serious model, and later behaviour is needed to separate them. Another candidate, ERASSTJ 045650.3-2 03750, has produced repeated X-ray and ultraviolet flares with a recurrence time that changed noticeably. 5 flares were reported, while the interval declined from about 300 days to around 230 days, and then toward roughly 190 days. Such a rapidly changing clock is difficult to explain with a perfectly unaltered orbit. Simulations suggest that a star may have lost a large fraction of its mass during the initial encounter, changing both its structure and motion. The case is especially valuable because X-ray observations can trace changes in the accretion flow close to the black hole, while the evolving recurrence time provides information about the survivor's orbit. Instead of showing a steady metronome, the system seems to be displaying a clock whose mechanism is being adjusted every time it ticks. AT2022DBL, also known as ASA SSN-22CI, produced 2 similar optical and ultraviolet flares separated by roughly 700 days. The spectra of the 2 episodes showed closely matching broad emission features, which strongly suggested that the same kind of debris and radiation environment had returned. Researchers described it as robust spectroscopic evidence for a repeated partial disruption, since 2 unrelated stars being destroyed in the same quiet galactic nucleus over such a short interval would be unlikely. The source was even nicknamed the unluckiest star, a description that is difficult to dispute. Yet the expected third bright flare did not appear in early 2026. Current modelling suggests that the star may still have been partially disrupted, but survived only long enough to create 2 observable episodes, or that later mass stripping produced a much fainter signal. Repetition, it turns out, does not guarantee indefinite repetition. A T2020 VDQ followed a similarly strange route. Its second major flare arrived roughly 3 years after the first, and was much faster and brighter, with extremely broad optical and ultraviolet features. That behaviour initially made it an important candidate for a repeating partial TDE, in which the second encounter removed more material than the first. The absence of a predicted third flare in early 2026 complicated the simplest periodic picture. A recent analysis argues that both AT202 OVDQ and AT202 2DBL can still be explained by survivors that underwent deep, early encounters and then produced only 2 outbursts bright enough to detect. Another study has questioned whether AT202 OVDQ might instead involve 2 separate stellar disruptions. The evidence continues to favour a connection between the flares, but the exact stellar history remains under discussion. These missing or irregular flares are not failures of the idea, they reveal how much the star and orbit can evolve. A survivor may lose so much mass during one passage that it becomes too faint to produce another detectable event. It may be completely destroyed on the second or third approach. A kick can move the next pericentre outside the strongest tidal region. Debris left from earlier encounters can alter how later gas circularizes and radiates. The accretion disk can change state quickly, because the amount of fuel is smaller than in a full disruption. X-ray bright repeating systems often move between luminous, faint, thermal, and harder spectral states on relatively short timescales, perhaps because the disk is repeatedly starved and refilled. The stellar orbit may be regular while the observed emission remains wonderfully uncooperative. A red giant can produce another kind of partial survivor. Its outer envelope is enormous and loosely bound, while its central core is compact. The black hole may strip away much of the extended gas without destroying the core. What leaves the encounter may no longer resemble an ordinary red giant. It could become a hot, exposed remnant with unusual surface composition and a greatly reduced radius. If it remains on a bound orbit, later passages may remove additional layers. Giant star encounters are particularly interesting because the tidal radius of the diffuse envelope can lie much farther from the black hole than the radius needed to destroy the core. One star therefore contains 2 very different disruption thresholds. Main sequence stars can survive too, but their long-term response depends strongly on internal structure. Higher mass stars often place a larger fraction of their material toward the centre, allowing them to lose small outer portions without dramatic expansion. Low-mass stars can be more vulnerable to runaway stripping. Removing material may cause the remainder to expand, so the next pass reaches farther into the star and removes even more. A sequence can begin gently and become destructive. Simulations of sun-like stars over repeated encounters show that tidal heating and mass loss restructure the survivor, sometimes leading eventually to complete disruption. A star can therefore survive the first pass and still be living on borrowed orbits. The material removed during a partial encounter has a different energy distribution from the debris of a complete disruption. Because a bound core remains, its gravity continues influencing nearby gas during and after the passage. Some matter that initially seemed stripped may fall back onto the star rather than the black hole. The surviving core can pull on the debris stream and modify the rate at which material returns. This can produce a steeper or more irregular decline than the familiar simplified fallback law used for full TDEs. Observationally, a partial disruption may fade quickly, shut off when the available debris is exhausted, or leave a low-level plateau from weakly bound material. The light curve contains a record of the survivor's gravitational influence, although extracting that record requires detailed models. The star may also carry away a distinctive rotation. Tidal torques can spin it up sharply during pericenter passage. A fast-spinning remnant is more oblate, with material at its equator less tightly held than material near its poles. On the next approach, the orientation of that spin relative to the orbit influences which layers are stripped. If the star's spin axis precesses between visits, the black hole may encounter a slightly different stellar shape every time. Recent work suggests that prograde spin, aligned with the orbital motion, can help explain systems whose flares steadily become fainter. The changing sequence is not merely a sign that the fuel reservoir is shrinking. It can be a measurement of the survivor's rotation. Repeated partial disruptions occupy an awkward region between a stable orbit and a one-time catastrophe. The star is stable enough to return, but unstable enough to lose mass. Its orbit is predictable enough to produce recurrence, yet each encounter modifies the conditions for the next one. This feedback creates several possible futures. A robust star can survive tens of passages while producing similar flares. A vulnerable star can lose progressively more mass and be destroyed after only a few. Another survivor may be kicked away from the tidal boundary and produce no further outburst. Some systems may show many low-level events that remain below survey detection limits, giving the impression of a single isolated TDE. There are stranger possibilities as well. A star might orbit one member of a binary black hole system, while the second black hole perturbs its path and the debris flow. Two stars from a disrupted binary could produce separate flares. A partial TDE inside an already active galactic nucleus can send debris into a pre-existing accretion disk, creating shocks and variability unlike those in a quiet galaxy. Some quasi-periodic X-ray eruptions, recurring over hours or days rather than months or years, may involve compact stars or stripped stellar cores transferring mass near a massive black hole, although several competing models remain. The broad family of repeating nuclear transients is likely to contain more than one mechanism, which is why astronomers are careful not to label every recurring flare as the same phenomenon. A genuine repeating partial TDE offers something especially valuable, a natural experiment that performs itself more than once. Ordinary TDEs provide only one observable destruction, and many important initial conditions are unknown. A repeating system allows astronomers to compare successive encounters involving the same black hole and the same surviving star. Changes in timing reveal orbital evolution. Differences in luminosity estimate how the stripped mass changes. Spectral variations show how the debris composition and accretion environment develop. A sudden absence of a predicted flare can be just as informative as a detection, because it may indicate complete destruction, a modified orbit, or a sharp reduction in mass loss. The recurrence period can also become a precision probe of the galactic center. Kepler's laws connect the orbital period with the size of the orbit and the black hole's mass. Relativistic precession alters the direction of pericenter. Frame dragging from a spinning black hole can twist a tilted orbit. Tidal energy deposited into the star can shorten or lengthen the period, while asymmetric mass loss can add small kicks. When a flare repeats many times, tiny changes accumulate into measurable shifts. A SAS-14 KOs, slowly changing recurrence time and the much faster evolution seen in J0456-20, are not merely scheduling details. They are evidence about forces operating where no spacecraft could survive. Partial disruptions may even be more common than the observed sample initially suggested. A flare from a grazing encounter can resemble a standard optical TDE so closely that astronomers may classify it as a complete disruption, unless the star returns during the available monitoring period. A T2022 DBL showed two remarkably similar, otherwise ordinary-looking TDE flares, raising the possibility that at least some events currently assumed to represent total destruction actually leave remnants behind. Recent simulations are actively testing whether a substantial fraction of detected TDEs could be partial. The answer will affect estimates of event rates, black hole feeding, stellar dynamics, and the kinds of stars that populate galactic centers. For the surviving star, there is no return to its old life. It may spend most of the orbit far from the black hole, appearing almost ordinary from a great distance, but its mass, spin, chemical layers, and internal temperature have been altered. Somewhere behind it, gas from the previous encounter is still accreting or moving outward. Ahead lies the same pericenter, unless the orbit is shifted enough to spare it. The next approach may remove a thin layer, produce a powerful flare, or finish the disruption. Astronomers cannot watch the remnant directly in most distant galaxies, but they can wait for the galactic nucleus to brighten again and compare the new signal with the old one. Those repeated signals turn stellar survival into a measuring device. A full disruption illuminates a black hole once. A partial disruption may trace the same gravitational field again and again, sampling the orbit under changing conditions. With each return, the survivor carries another piece of information through the black hole's tidal field, leading us toward the wider question of what these rare events can reveal about otherwise invisible black holes and the galaxies built around them. The returning flare reveals more than the destruction of one star. For a short time, it turns an otherwise hidden region of a galaxy into a laboratory. The star supplies the material, the black hole supplies the gravitational field, and the radiation carries information outward. Astronomers receive that information long after the encounter and use it to investigate an object that may have produced almost no detectable light before the star arrived. A tidal disruption event is therefore both a catastrophe and an opportunity. The star is lost, completely or partially, but its debris outlines the black hole's influence in a way ordinary starlight cannot. By measuring how the flare rises, changes and fades, researchers can estimate the black hole's mass, study matter moving through strongly curved space-time, examine the population of stars near galactic centers, and search for black holes in galaxies whose nuclei normally appear quiet. A black hole does not need to be actively feeding all the time. Many massive black holes may spend long periods with very little gas falling toward them. Without a luminous accretion disk, they are difficult to detect directly. Astronomers can sometimes infer their presence from the motion of nearby stars or gas, but that becomes increasingly difficult in distant galaxies. Individual stars cannot be resolved easily, and the central region may occupy only a tiny fraction of one telescope pixel. A TDE changes the situation. The black hole receives a sudden supply of stellar material, and the surrounding gas produces a bright flare. The previously hidden black hole announces itself, not by emitting light from inside the event horizon, but by changing the motion and temperature of matter outside it. This makes tidal disruptions especially useful for finding dormant black holes. An active galactic nucleus already reveals that a central black hole is feeding. Its persistent radiation may continue for thousands or millions of years, although the brightness changes over shorter intervals. A quiet nucleus offers no such obvious signal. When a star is disrupted there, the temporary flare confirms that a strong central gravitational source exists. The event may last only months or years, but it exposes a black hole that could otherwise remain unnoticed for much longer. The mass of that black hole can be estimated in several ways. Properties of the host galaxy provide one route. The speed at which stars move through the galactic bulge is related statistically to the mass of the central black hole. The brightness and mass of the bulge can offer additional estimates. These relationships were originally developed using galaxies with black holes massive and active enough to measure through other techniques. TDEs allow astronomers to test and extend them towards smaller black holes and fainter galaxies, where the existing relationships are less certain. The flare itself contains an independent set of clues. The time required for the most tightly bound debris to return depends partly on the black hole's mass and the structure of the destroyed star. A more massive black hole changes the orbital period of the returning gas. The temperature of the inner accretion flow also depends on mass. Rapid fluctuations in X-ray brightness limit the size of the emitting region and can indicate how quickly material is orbiting close to the event horizon. By comparing these signals with physical models, astronomers can estimate the black hole's mass even when the host galaxy is difficult to study in detail. This is particularly valuable at the lower end of the massive black hole population. Supermassive black holes with millions or billions of solar masses are known to occupy the centres of many large galaxies. The situation becomes less clear in small galaxies. Some may contain black holes of hundreds of thousands of solar masses. Others may host intermediate mass black holes, a broad and still incompletely mapped group between the black holes formed by massive stars and the supermassive objects found in large galactic nuclei. Some small galaxies may contain no central black hole at all. Determining how frequently low-mass galaxies contain black holes can help scientists understand how the first black holes formed. One possibility is that the early universe produced relatively small seeds from the deaths of the earliest massive stars. Those seeds then grew through mergers and accretion. Another possibility is that large gas clouds collapsed directly into heavier seeds, giving some black holes a substantial head start. The number of black holes present in modern dwarf galaxies, along with their masses, may preserve evidence of those different beginnings. A faint galaxy with a quiet central black hole may reveal almost nothing under normal conditions. If one of its stars is disrupted, the flare can make the black hole visible across a large distance. The event effectively places a temporary marker on the nucleus. Astronomers can then estimate the host galaxy's mass and compare it with the inferred black hole mass. Repeating this process across many TDEs begins to map a population that ordinary active galaxy surveys may miss. There is an important selection effect, however. A black hole must have the right mass to tear a particular star apart outside its event horizon. If the black hole is too small, the disruption may be relatively faint or evolve quickly, making it easy to miss. If it is extremely massive, a sun-like star can cross the event horizon before producing a bright external disruption. In that case, the black hole gains material, but the wider universe receives little radiation from the destruction. The disappearance may be dramatic locally and observationally quiet from far away. This upper limit is sometimes connected with the Hills mass, named after astronomer Jack Hills. It is not one exact number for every event. The boundary depends on the star's size and density, the black hole's spin, and the direction of the orbit. A rapidly spinning black hole changes the location of the horizon and the innermost permitted orbits relative to a non-rotating one. A giant star, with its expanded outer envelope, can be disrupted outside the horizon of a black hole that might swallow a smaller star more directly. Even so, the decline in observable TDEs around the most massive black holes provides a way to test the expected boundary between visible disruption and direct capture. Black hole spin may leave other clues. A spinning black hole drags nearby space-time around with it. This frame-dragging effect changes tilted debris orbits and can cause an accretion flow to precess. The location of the innermost stable circular orbit also depends on spin. Gas orbiting in the same direction as the black hole's rotation can remain stable closer to the horizon than gas orbiting around a non-spinning black hole. Because matter can move deeper into the gravitational field before plunging inward, it may release more energy. Measuring spin is difficult. The flare must be modelled carefully, and uncertainties in the debris geometry can imitate some of the same observational effects. Yet certain TDEs provide promising possibilities. Stable or repeating X-ray variations may come from material moving near the innermost orbits. Changes in the shape of an X-ray spectrum can reflect the temperature and size of the inner disk. A precessing jet or tilted flow may cause brightness to change in a regular way. None of these measurements is simple, but TDEs bring fresh material close enough to the black hole for spin to matter. General relativity also affects the debris long before it reaches the horizon. The returning stream does not follow a perfectly closed Newtonian ellipse. Its orbit precesses, shifting the path after each closed passage. That shift helps the stream collide with itself, creating shocks and beginning circularization. By observing how quickly a disk forms and where the main radiation appears to originate, researchers test calculations of orbital motion in strongly curved space-time. A TDE takes a star, spreads it into a long stream, and sends different parts of that stream along trajectories shaped by relativity. The resulting flare is an indirect map of those paths. In this sense, the destroyed star behaves like a large collection of test particles. Before disruption, all its material travelled together. Afterward, the gas occupies a broad range of energies and orbital periods. Some debris escapes, some returns quickly, some takes much longer. The black hole sorts the stellar material according to its position during the encounter. Astronomers then watch the sorted material come back, collide, radiate, and gradually disappear. The behaviour of the debris also teaches us about accretion. Black holes grow by receiving matter, but astronomers cannot usually watch an accretion flow form from a clearly defined beginning. An active galactic nucleus may already have contained a disk for a very long time before observations began. Its source of fuel can be complicated and continuous. A TDE provides something closer to a natural controlled experiment. A quiet black hole receives a sudden, limited supply of gas from one star. Researchers can follow the appearance of shocks, the development of a disk, the formation of a hot corona, the launch of winds, and, in rare cases, the creation of a relativistic jet. Different wavelengths trace different stages. Optical and ultraviolet light may reveal stream collisions or radiation reprocessed by an extended debris layer. X-rays can probe the compact inner flow. Radio emission follows outflowing material as it moves into the surrounding galactic gas. Infrared echoes measure dust farther from the centre. Combining these signals produces a time-dependent picture of black hole feeding across a large range of distances. This process may also improve our understanding of why some black holes launch jets while others do not. A jet requires more than material falling inward. Strong, organised magnetic fields are likely important, and black hole spin may supply additional energy. A disrupted star delivers both matter and embedded magnetic fields, but those fields begin on stellar scales, rather than in the large ordered arrangement needed near the black hole. Researchers study whether turbulence and rotation can amplify and organise the field quickly enough. The rarity of obvious jetted TDEs suggests that the required conditions are not achieved in every disruption, although viewing angle hides many jets that point away from Earth. Outflows from ordinary, non-jetted TDEs matter as well. Radiation pressure and shocks can drive broad winds that carry stellar material back into the galactic nucleus. These winds may heat or push away surrounding gas. One event will not transform an entire large galaxy, but repeated disruptions over long times could contribute to the exchange of matter and energy near the centre. TDEs therefore connect the fate of individual stars with the environment from which future stars may form. The debris contains chemical information too. The star spent much of its life turning hydrogen into helium, and depending on its mass and age, altering the abundance of carbon, nitrogen, oxygen and heavier elements in its inner regions. A disruption exposes material that would normally remain hidden beneath the stellar surface. If gas from deeper layers enters the accretion flow, its spectrum may carry signs of nuclear processing. Strong nitrogen features in some TDEs have been interpreted as evidence that the destroyed material experienced the carbon-nitrogen-oxygen cycle inside a star. The exact interpretation depends on ionization and radiative transfer, so spectral lines cannot be read as a direct inventory without modelling. Even so, a torn star can give astronomers a rare view of material from below a stellar surface in a galaxy far beyond our own. Partial disruptions extend that opportunity. A surviving star may lose different layers during successive passages. Early flares may be dominated by the original envelope. Later encounters may expose more processed material from farther inside. Changes in the spectrum could therefore trace the progressive removal of the star. The black hole performs a rough form of stellar dissection, one orbit at a time. TDS also reveal the stellar population around the black hole. The event rate depends on how many stars occupy the central region, how densely they are packed, and how their orbits are distributed. A galaxy with a dense nuclear star cluster can scatter stars toward dangerous trajectories more frequently. A spherical and dynamically relaxed cluster produces one pattern of encounters. A flattened, rotating, or recently disturbed central population may produce another. Each disruption begins because a star's angular momentum becomes small enough to place it inside the loss cone. Counting TDEs helps astronomers test how efficiently stars enter those orbits. If observed rates exceed predictions, the galactic centers may contain structures missing from simplified models. Massive perturbers, stellar binaries, elongated orbital distributions, or pairs of central black holes could all increase the supply of stars moving toward the tidal radius. One of the strongest demographic clues is the unusual frequency of TDEs in galaxies that recently ended a major episode of star formation. These post-starburst galaxies contain many stars formed within the past billion years or so, but comparatively little ongoing star formation. Their spectra record the presence of a young stellar population even though the burst has faded. Although such galaxies are not the most common kind in the nearby universe, they have appeared disproportionately often among TDE hosts. The reason remains an active question. A recent galactic merger may concentrate stars near the nucleus. It can also disturb their orbits, leaving an elongated or asymmetric central structure that directs more stars toward the black hole. If the merging galaxies each contained a central black hole, the resulting pair could scatter stars efficiently before eventually combining. Dense populations of relatively young stars may provide another contribution. The enhanced TDE rate may therefore preserve evidence of a galaxy's recent structural history. A flare lasting only months can reveal an event that reshaped the host galaxy hundreds of millions of years earlier. The connection is indirect but important. A merger compresses gas and triggers star formation. That burst ends. The central stellar population settles into a new arrangement. Long afterward, the changed orbits increase the chance that a star will reach the black hole. The TDE becomes a delayed consequence of galactic evolution. Binary black holes are particularly interesting in this context. When galaxies merge, their central black holes should gradually move toward the common center and form a bound pair. Directly identifying such systems at small separations is difficult. Their orbital motion may not be resolved, and both black holes may be quiet. Yet a binary changes the paths of nearby stars and can interrupt or distort tidal debris streams. An unusual TDE-like curve might therefore reveal a second black hole indirectly. The flare may fade abruptly when the companion disturbs the returning stream. Debris may be delayed, redirected, or separated into episodes. Repeated observations are needed because ordinary accretion changes can produce similar behavior. Still, a growing sample of well-monitored TDEs could help identify galaxies containing black hole pairs that are approaching an eventual merger. Those mergers are expected to release gravitational waves at frequencies different from the signals produced by stellar mass black holes. Future space-based gravitational wave observatories are intended to detect the motion and merger of massive black holes across the universe. TDEs can complement those observations by identifying galaxies where central dynamics appear disturbed. The torn star and the gravitational wave would probe different parts of the same long galactic process. TDEs also help investigate black holes displaced from the exact centers of their galaxies. The simplest picture places one massive black hole at the nucleus. Galaxy mergers can produce more complicated arrangements. A black hole may orbit away from the center after interacting with another black hole. A gravitational wave recoil generated during a merger can push the final black hole from the nucleus. Small satellite galaxies can bring their own black holes into a larger system. A tidal flare appearing noticeably away from the visible center may reveal one of these wandering black holes. The positional measurement must be precise because an ordinary supernova can also occur outside the nucleus. When the spectrum and multi-wavelength behaviour support a TDE interpretation, the offset becomes evidence that a massive black hole is moving through the galaxy rather than resting at its centre. Such discoveries expand the idea of where massive black holes can be found. This has consequences for black hole growth. A displaced black hole may receive less gas than one settled in a dense nucleus. It may carry a small group of stars with it, occasionally disrupting one. Its motion through the galaxy can affect surrounding gas and star clusters. By discovering off-centre TDEs, astronomers can identify black holes whose existence would otherwise remain hidden among the galaxy's ordinary light. The increasing number of wide-field surveys is turning isolated discoveries into population studies. Earlier TDEs were often found by chance in X-ray or ultraviolet observations. Modern optical surveys repeatedly scan large areas, producing systematic samples. Future surveys with deeper images and more frequent coverage should find many more, including fainter and more distant events. A larger sample will help separate genuine physical patterns from observational bias. Optical surveys favour flares with bright visible emission and low dust obscuration. X-ray surveys find hotter events, but may cover the sky less frequently. Radio searches are most sensitive to energetic outflows. Infrared surveys can discover events hidden behind dust. Combining them is necessary to estimate how often stars are truly disrupted and how many events each method misses. With enough detections, astronomers can map the black hole mass function, meaning how the number of black holes changes across different masses. Active galaxies provide part of this information, but they select black holes that are currently receiving gas. TD select black holes through the stellar population around them and their ability to disrupt stars outside the horizon. The two methods have different biases. Together they produce a more complete view. Distant TDEs can also show how black hole populations changed over cosmic time. Looking farther away means looking further into the past because light requires time to travel. A flare observed in a galaxy billions of light years away occurred when the universe was younger. If surveys collect enough distant events, researchers can compare disruption rates, host galaxies, and black hole masses at different ages of the universe. The interpretation will be challenging. Distant flares appear fainter. Cosmic expansion stretches their wavelengths and makes their evolution look slower. Their host galaxies are harder to resolve. Selection effects become stronger. Even so, a bright TDE can serve as a beacon from a black hole that would otherwise be too quiet to study. One star's destruction may briefly expose a galactic nucleus from a period when black holes and galaxies were still developing toward their modern forms. This returns us to a larger relationship. Massive black holes contain only a small fraction of a galaxy's total mass, yet their properties are closely connected with the stars around them. More massive galactic bulges tend to contain more massive central black holes. The reason is not simply that the black hole's gravity controls the whole galaxy. Far from the nucleus, stars and dark matter dominate the motion. Instead, black holes and galaxies appear to grow through related processes involving gas inflow, star formation, mergers, accretion, and energetic feedback. A TDE captures that relationship on a small scale. One star, formed from galactic gas, eventually reaches the central black hole. Part of its material is accreted, part is expelled. Radiation and winds return energy to the surroundings. The black hole gains a little mass, while the galactic nucleus receives redistributed gas and heat. The event is minor compared with the entire lifetime of the galaxy, but it demonstrates the exchange between stars and the central black hole directly. The star's fate is extreme, although the physics begins with familiar gravity. There is no separate black hole force invented only for dramatic occasions. The same gravitational principle that keeps the Moon orbiting Earth and Earth orbiting the Sun shapes the stellar encounter. What changes is the gradient. Across a human body on Earth, the difference in gravity is tiny. Across a star passing near a massive black hole, the difference becomes strong enough to separate the star into debris. This is one of the most useful lessons contained in a TDE. Gravity does not need to strike an object to destroy it. It changes motion. Near the black hole, neighbouring parts of the star are directed onto sufficiently different paths that the star's internal forces can no longer keep them together. The destruction is a consequence of geometry and distance. The nearer side falls faster, the farther side falls more slowly, and an object that survived for billions of years loses its shape during one passage. The black hole remains dark throughout. The flare does not reveal the interior. It marks the boundary between what can still communicate with the universe and what cannot. Gas outside the event horizon collides and shines. Material that crosses the horizon stops contributing new signals to distant observers. Astronomers watch radiation from the last region where the star's matter can still announce its presence. Darkness around a black hole is therefore not emptiness. The region can contain stellar orbits, magnetic fields, thin gas, old debris, dust and radiation passing through from elsewhere. It appears dark because the black hole itself emits no light, and because a quiet surrounding environment produces little radiation. The arrival of a star changes the environment temporarily. The hidden gravitational structure becomes visible through its effect on matter. Eventually the flare fades. The returning debris supply decreases because the most tightly bound material has already completed its orbit. Gas that returns later is more weakly bound and arrives at a lower rate. Winds thin. The optical photosphere shrinks. X-rays may continue from a faint inner disk, then weaken. Radio emission from the outward moving shock may remain detectable after the central light has declined. The host galaxy slowly returns to its earlier appearance. In ordinary images, the central point blends back into the surrounding stars. The black hole has gained some fraction of the stellar mass, but the increase is tiny compared with its total size. Escaping debris moves into the galactic nucleus. Dust that was heated by the flare cools. The temporary laboratory closes, leaving observations and archived data behind. From Earth, the ending is gradual. There is no single final photon labelled as the last piece of the star. Light continues arriving from different regions. The central disk produces one fading signal. Expanding gas creates another. Dust echoes repeat earlier radiation after a delay. Radio waves emerge from shocks moving through the surrounding environment. The star's observable end is spread across wavelengths and time. Much of its matter may never enter the black hole. The unbound tail escapes. Winds carry additional gas outward. A partial survivor may retain a core and return. Even during a complete disruption, the phrase swallowed by a black hole simplifies a much more complicated division. The star is separated among several futures. Some matter becomes part of the black hole. Some remains in orbit. Some is expelled into the galaxy. Its energy leaves as radiation, heat, and motion. The atoms themselves do not vanish when the star loses its identity. Hydrogen and helium that once occupied the stellar envelope may drift outward in the debris. Heavier elements from deeper layers can mix into the galactic center. Material crossing the horizon becomes inaccessible to outside observers, but the black hole's mass increases accordingly. Conservation laws continue operating throughout the disruption. The star ends as an organized object, not as physical substance removed from reality. That distinction changes how we think about stellar death. Stars can end in several ways. Some gradually release their outer layers and leave white dwarfs. Massive stars collapse and explode, producing neutron stars or black holes. Binary stars exchange material, merge, or trigger thermonuclear explosions. A TDE is different because the cause comes from the star's orbit, rather than from the exhaustion of its core. The star may have had millions or billions of years of normal life remaining. It is destroyed because its path brings it into the wrong gravitational region. There is no intent in that path. The black hole is not hunting. The star is not being punished for wandering. Both objects follow gravity. Other stars alter the orbit slightly. The lost cone receives a new member. The star approaches, the tidal gradient increases, and the internal balance fails. Scientific language sometimes makes the event sound personal, because words such as feeding, swallowing, and devouring are easy to understand. The actual process is governed by motion, energy, pressure, and space-time. Knowing this makes the event less like a cosmic monster story, and more like an unusually clear demonstration of physical law. The black hole is extreme, but it behaves consistently. The star's disruption can be calculated, simulated, and compared with observations. Models are incomplete, especially when dealing with circularization, radiation, magnetic fields, and partial survivors, but the broad sequence is understood. A star passes inside the tidal radius. It is stretched and compressed. Its debris receives a range of orbital energies. Bound gas returns. Collisions and accretion release radiation. The flare fades as the supply decreases. During our journey, we began with a steady star approaching a dark galactic center. We followed the small orbital changes that placed it in danger. We watched the tidal force become strong enough to defeat the star's self-gravity. The star lengthened through spaghettification, not because the black hole touched it, but because gravity differed sharply across its width. Its material separated into streams, some escaping and some returning. Those returning streams wrapped around the black hole. Relativistic precession shifted their paths and helped them collide. Shocks changed organized motion into heat. Gas began forming an accretion flow, while winds pushed part of the debris outward. The central region brightened in visible light, ultraviolet, X-rays, and sometimes radio emission. In rare cases, a relativistic jet carried energy away at nearly the speed of light. Astronomers detected the flare as a changing point near the center of a distant galaxy. They measured its position, temperature, spectrum, and timing. They compared optical images, followed ultraviolet light from space, searched for X-rays near the event horizon, and listened with radio telescopes for the expanding outflow. From those separate signals, they reconstructed a destruction too distant and too small to photograph directly. We also followed the stars that survive. A partial disruption can remove an envelope while leaving the dense core intact. The remnant moves outward, altered in mass, rotation, temperature, and structure. If it remains bound, it returns. Another passage removes more gas and produces another flare. Some survivors endure repeatedly. Others are destroyed after only a few encounters. Their changing outbursts allow astronomers to measure orbital evolution in real time. Now the wider purpose of those observations becomes clearer. A TDE can identify a dormant black hole, estimate its mass, provide clues about its spin, test motion in curved space-time, and reveal how accretion begins. It can expose the density and history of a galactic nucleus. It can hint at black hole pairs, displaced black holes, and the aftermath of galaxy mergers. A torn star becomes a source of information about structures much larger than itself. The event also places our own surroundings in perspective. The Sun is not moving toward the central black hole of the Milky Way. It follows an orbit far from the galactic center, in a region where the black hole's tidal influence across the solar system is negligible. Stars must pass extremely close to a central black hole to be disrupted. Most never do. The galaxy is not a funnel in which everything gradually spirals toward the middle. Stable orbits are common, and the vast distances between stars make destructive encounters rare for any individual object. That is useful to remember as the room around you becomes quieter. Somewhere in the observable universe, tidal disruption events are occurring, but they are separated from us by enormous distances. Their radiation may travel for hundreds of millions or billions of years before reaching our telescopes. By the time one is detected, the central flare in its home galaxy may already have faded. Astronomy receives the old report, not the immediate danger. The photon entering a telescope may have begun its journey when the star's debris was still hot and dense. It crossed the host galaxy, travelled through intergalactic space, and continued while stars formed, planets changed, and life on Earth followed its own history. Eventually, a mirror collected it. A detector converted it into an electronic signal. Software compared it with earlier images, and an astronomer recognized that a distant galactic center had brightened. From that small measurement grows the entire reconstruction. The point of light becomes a star's altered orbit. Its color becomes a temperature. Its spectrum becomes moving hydrogen and helium. X-ray variations become gas near a horizon. Radio waves become an outflow crossing the nuclear environment. The event is never seen from close range, yet physical laws allow the pieces to be connected. Perhaps that is one reason these events are so compelling. They show how much can be learned from something that cannot be approached, repeated deliberately, or viewed directly. Astronomers work with delayed light and incomplete evidence, but the evidence is not meaningless. Every photon has been changed by the material that emitted, absorbed, scattered, or redirected it. Careful measurements recover part of that history. A tidal disruption event begins with darkness and briefly creates light. The black hole remains invisible, yet its gravity determines everything. The star stops shining through fusion as an organized sphere and shines instead through shocks, accretion, and heated debris. Its final radiation is not produced by the life process that supported it for so long. It comes from the loss of that structure. There is something sobering in the difference between those timescales. The star may have spent billions of years in stable balance. Its disruptive passage lasts hours. The debris flare continues for months or years. Then the galaxy appears quiet again. A long stellar life is converted into a short astronomical signal, and that signal travels outward much longer than the disruption itself lasted. Yet the event is not wasted motion. The returning gas teaches us how matter behaves close to a black hole. The escaping material joins the galactic environment. The flare identifies a hidden object and adds another measurement to the history of black holes and galaxies. The star's organized life ends, but the information carried by its final light continues travelling. As you rest here on Earth, you're also made from material that has passed through earlier generations of stars. The heavier elements in the planet, in the room around you, and in your body were created or redistributed through ancient stellar processes. A TDE is not the main source of those elements, but it belongs to the same continuing movement of matter through stars, gas, gravity, and galaxies. Nothing in a galaxy remains permanently isolated. Orbits change, stars evolve. Gas is exchanged, black holes grow, new stars form from material shaped by older ones. Tonight, however, there is no need to follow that cycle any farther. We have stayed with one star from its final safe orbit to the last fading signals of its debris. We have watched a dark object become visible through the light of something it destroyed. We have seen that a black hole's darkness is not a failure of science to observe it. It is a property that can be studied through motion, radiation, and the behavior of surrounding matter. So let me ask you once more, gently, where are you listening from tonight? What time is it in your small part of the galaxy? Perhaps the hour has moved farther along than you expected. Perhaps the room feels quieter now. While we have been following debris around a distant black hole, Earth has continued turning, the Moon has continued along its orbit, and the Sun has continued carrying the solar system through the Milky Way. If this journey gave your thoughts somewhere calm to settle, you can like the video, subscribe, and share this quiet space with someone else who enjoys letting science take the slower route. There will always be another strange object to visit, another distant signal to examine, and another ordinary physical law behaving in an extraordinary environment. For now the flare is fading. The returning stream has grown thin. The brightest debris has already released its energy, and the central point of the distant galaxy is becoming quiet. The black hole remains where it was, slightly heavier and once again difficult to see. Around it, the scattered material of the star follows new paths, while the last radiation continues outward through space. Long after that galactic centre returned to darkness, part of its light reached us. We collected it, measured it, and learned what happened. A star passed too close. Gravity separated it. The debris briefly illuminated the hidden black hole and revealed something about the galaxy around it. Then the light moved on. Here, far from that event, there is only the steady room around you, the surface of a safe planet, and the familiar pull of gravity holding everything where it belongs. Let the distant flare fade from view. Allow the black hole to return to silence, and as your thoughts slow with it, sleep well, fellow traveller, beneath a sky filled with old light and safely distant darkness.